All right, so Unit 1, the fundamentals of electricity. I think you'll love and hate this because it's going to be really technical and kind of scientific and a little geeky. And it's not exactly going to help you fix the car, but you have to know this to learn the stuff so you can fix the car, okay? So right off the bat, I want to make sure you understand, if you say you're not going to work on electrical systems, you're just going to do, who wants to just do like engine work, engine building? Well, that's got a lot of electrical. You can see transmission, steering, suspension, braking, engine control, emissions, navigation. It's all electrical, everything.
What if I want to specialize in old engines?
If you want to work on older stuff, there's less electrical, that's true, and there's also a lot less jobs.
Yeah.
And there's also probably a lot less money in that. Unless you had like an amazing name for yourself and you were some hot rod builder, like if you're Chip Foose or something and you're designing and you got people that are building, maybe. But for you to try to be entering the industry, that's a totally defective thought. You gotta be able to work on all this electronic integrated stuff. And if we really wanted to add here, the big one would be if the car is hybrid or electric, it's obviously got a lot of electric, but even if it's not, like you guys think of the least electric car that they're making right now. What's the least EV? What's the anti-EV car? Like what, the Hellcat?
Yeah.
Still tons of electricity and electronics in that car, tons.
This LS, right?
Sure, no, that's like a supercharged Dodge, yeah. There you go. With a big supercharger now. Yeah. Actually, the Camaro's now at LT, but that's a LT. All tons of electronics. That's my point. Okay. And so we're gonna kind of go over some of the electrical stuff, and then here's a little bit of a little bit more of a selling point. So if you're gonna work on, what's it say, a modern vehicle, you're gonna need to know everything that you're learning in this class, okay? It's very important. You need to understand electrical and electronics. So right here I wanna tell you the difference. Electrical is more kind of like the battery, the starter, the alternator. If you look at like the wiring itself, a lot of lights, like a light bulb is an electrical component, but when they say electronic, that's more like a little printed circuit board, you know, a module. Oh, sensors a lot of times can be kind of a mix, electrical, electronics. So if you ever hear them say, you know, electrical systems or electronic systems, they sound the same, but they're actually a little bit different. And we're gonna cover both, and you need to understand both. So let's say like in one example, who here has ever had a taillight go out? On some cars, a taillight is as simple as a switch sends voltage to a bulb, and the bulb glows when it gets 12 volts in ground. Okay, or on some cars, a taillight is you turn on a switch, the switch gives a signal to a computer like a body control module. The body control module then sends voltage to, let's say, a relay, or in some cases a transistor. And then the transistor is going to send the voltage to your taillight, which is actually going to be an LED. And when we say an LED, it's not just an LED, it's like a circuit board with multiple LEDs and controllers and stuff. So that's electronics. So it could be like a more of a basic electrical, or it could be a full-blown computer-controlled lighting circuit. That's electronics. And you're going to be using different tools and just kind of like a different way to approach that. So with the electrical, if you want to test the switch, you probably use your meter. Electronics, if you want to test the switch, remember that's an input to a computer. I'd probably go first to the scan tool, open the scan tool up, look at data, turn the switch on and off, and I'd see if the computer is seeing the switch on and off. You'll actually see it on screen, right? So the way you diagnose this is a bit different than this, but sometimes you gotta do both on the same problem on the same car, okay? And then obviously we're talking about if you want to work on the current vehicles and the future vehicles, you absolutely have to have a solid understanding of electrical terminology, the behavior, the components, the theory. You have to really know all this stuff to be able to work on even a car that's 20, 30 years old, but definitely a car that's present, that's new. Okay, And then also, you need to be able to read wiring diagrams, measure electrical quantities, so volts, amps, ohms, diode testing. You know, we could, electrical too, a lot of times we'll get into like frequency, hertz, duty cycle, a lot more advanced stuff. In the shop, calculate electrical values and understand the quantities used. So you have to understand this relationship. And the relationship gets a little scientific geeky, where it's like Ohm's law. If we increase the voltage, what happens to the amperage? Or more commonly, when you have a problem, if you have excessive resistance, what does that do to the circuit, right? There's a cause and there's an effect. So if you have a symptom of a headlight, and the headlight is kind of dim, right? You got one headlight that's bright, and you got one headlight that's dim. If I were to just look at that, I'd say, oh, the dim one has excessive resistance in the circuit. Where? I don't know. But when I go after it, I'm going to be basically testing for excessive resistance. Make sense? So that I can find it. And if I find it, I can fix it. But you can test resistance in several ways. So you could test resistance with your meter on resistance, on the ohm setting, and that works. But actually there's a better way to do it, and you could test available voltage at multiple points and calculate voltage drop. Or you can measure voltage drop, and the voltage drop indicates the excessive resistance. And you're thinking like, what the heck? So we're going to spend a lot of time kind of building up on this so you can understand it a little bit more, okay? Quite a bit. Now, what is electricity? It's the movement of specific particles, electrons, right? So we're gonna move some stuff from one point to another. It can perform work. So that's where we found electricity to be useful. Electricity's always been a thing. So for example, if you were to take your shoes off and slide across a carpet, you can do things with electricity, with static electricity. I guess that's kind of work. If you want to shock somebody, it is fun. So you're doing work right there. But generally, we figured out, hey, here's how we can take electricity, we can control it, we can have it do things. So this will get into it, but like we're relying on these lights right now. This computer's working on electricity, so we're taking the movement of these electrons, controlling them in a certain way, and doing work. Who can give me one other example of how we do work with electricity? One more. It's okay.
What was the question?
Give me one more example of how we do work using electricity. Welding is one thing. That's true. So we actually make a high enough current to melt a metal, and then that metal will melt into other metals, and you can join two pieces of metal together. That's one thing that electricity can do for work. That's true. True. So what about let's say, anybody got a space heater at home? Space heaters are pretty nice. That's work. You're taking electricity, you're making heat. It's doing work for you. Mason is going to get himself an e-bike and a pair of goggles like this. And that e-bike is going to put in some work. So we're going to take electricity, we're going to basically use it as a motor using, basically we're going to get into like magnetic fields, but we can use electricity to make a magnetic field to attract and repel and make a motor turn a sprocket, turn a chain, turn a rear wheel, and get Mason to school. Like, we could use electricity for lots of stuff. And so that's kind of what it's saying here when we get into attracting and repelling, right? So basically, electricity can be used for work. The moving electrical particles carry a negative charge, and they're attracted to a positive charge. Okay, so this is the fact, but sometimes the way we talk about it is a little bit opposite. In reality, this is a battery right here. And just for reference, this is the negative side, and this is the positive side. There's an excess of electrons on the negative side. They really, really, really badly want to get to the positive side because there's a whole lot of negative charge here, and they're constantly trying to get to be like even. Like if these electrons want really badly to get over here, if you were to discharge this battery, eventually end up where there's the same electrons over here and the same electrons over here, and there's no longer any electrical potential, that's voltage. So this voltage would be 0. So these electrons on the negative really want to go to the positive. And that's electron theory. And that's, as far as we know, that's the accurate one. But the way I'm going to teach the class and the way that you're going to understand it and the way that basically all automotive technicians understand it is it goes from positive to negative. I'm just letting you know that's not actually true. I'm sorry. On our diagrams, you trace it positive, negative. Everything's designed on positive, negative, but in reality, just let you know, you can't ever see it with your eyes, but the electrons are actually going negative to positive, okay? So just for now, for the scientific theory, I want you to know that. And we can make them do work while they're trying to go from that negative to positive, cool? So let's talk about more sciencey stuff. You guys know matter is everything. So if someone says like, what's the matter? You just say like everything with size and weight. Okay, that's what's the matter? I can't fix that. Makes sense, but matter is going to be atoms. So if you look at atoms, you got protons and neutrons. We're not super concerned about those in electricity. What we are concerned about is these. You guys have at least heard this before, right? Because I don't really know what they'd be teaching in school right now. You know there's atoms. The electrons are going around, but we're actually going to focus a lot on these electrons, which have a negative charge, and how we can have a move from one atom to the next, to the next, to the next. So if we were to zoom in really closely, electricity is the study of these things and what they do and how we can make them do it, right? And then they're moving around the nucleus, so that's what we're saying. And then they travel in different rings, and that's going to be something that is important when we talk about like conductors and insulators. So sometimes the electrons are in like the tighter rings, and sometimes they're way out here, like in the valence ring, like on the outside. Cool. Okay. Now each ring, so there's the inner rings and the outer rings, can contain a specific maximum number of electrons. Okay, just so you know. And then if basically we had an equal number of protons and electrons, the charges cancel each other out, which means it has like no charge, it's neutral. Make sense? But we could have an atom that has more electrons than the protons, and that's going to have a negative charge. Does the negative charge sound balanced? So if you have like a checking account and it's negative, is that balanced books? That's not a good thing, right? There's some problems there. So what that would mean is the negative ion is not balanced, so it's looking for a change. You know what that means? It's kind of like, hey, I'm in the negative. When your bank account's in the negative, you're trying to tell me that you're not looking for a change? You're like, let me put some money in there, because you know what's coming, right? Those overdrafts and all that. Oh my good. So it's kind of the same with these atoms. If they're excessively negative, they're looking to make a change. They're willing to let some of those negatives go. That's kind of what I'm telling you. So look, the electrons have the same negative charge and they repel one another. The repelling force wants to push one of the electrons away. So it's kind of like this debt, like get rid of this debt. That electron is already about to be pushed out. Make sense? So once you have it negatively charged, it's ready to let some of those electrons go. So this one would be a negative ion. So if you look, there's protons and neutrons, but then look, there's a bunch of electrons. Like in this case, there's 3. There's more negatives than there are positives. You guys can see that, right? 2 protons, how many electrons? 3. So this is not balanced, it's negative. It wants to be balanced. So you know what? It's already like one of these, it's trying to say, let me get out of here. Get out of here. Doesn't it seem like it'd be pretty easy to move one of those electrons out? Good, we're gonna do that. Okay? Here's a positive ion. Proton. How many electrons?
1.
Okay, exactly. You know what would be perfect? Look at this. This one could jump right over here and they'd both be happy. Naturally in nature, like as it exists, that's what wants to happen. That's what's naturally trying to occur. It's pretty crazy if you think about it. Like, wow, that's amazing. How did that happen? And yet, there you go. Now, if we get into conductors and insulators, who can give me an example of one good conductor? I'm talking about on the periodic table of elements, or You know,
Water.
copper's good, water's decent, copper's good, aluminum,
aluminum.
gold's amazing, silver. So like some people would say the economy's sketchy and, you know, be ready for the fallout and whatever, buy gold. And it's sort of like, why gold? I mean, we're not making our coins out of gold anymore and stuff like that, and it used to be the standard for how we based our currency, but now gold is like, what value is gold really? Well, I can tell you, I'm not recommending an investment. I'm not an investment guy. If it was me, I'd probably buy land and houses because they're not making any more land and people need a place to live. However, you pay a lot of taxes and there's some problems there. But if you bought gold, gold is always going to be used and in demand for electricity, electronics, these types of things. Airbags, for example. You guys have airbags in your car. I'm not talking about I'm talking about like supplemental restraint systems. If you get in an accident, first off, your seatbelt's supposed to help. But secondly, the supplemental restraint system, the helping restraint system is the airbag. A lot of those airbags, all the connectors, everywhere there's a connector and you have like a terminal connection, they'll use gold-plated terminals on airbags because it's so critical and it's such a safety thing. They're like, hey, we could use aluminum, but for airbags, let's use gold. You know, so gold does have some really serious value and benefits in electronic systems, okay? So whatever that, actually, I don't know what this one is. CU.
That's copper.
Is it copper?
That is copper.
I believe you. Look at copper. It's got all these electrons. And look at this one electron on the outer valence ring. It's going to be super easy to pop that sucker off of there. Make sense? So when you want to have electricity flow, remember, it's the flow of the actual electrons. And here you're looking at copper, and you're like, that one, with just the slightest push, that sucker would be out of there. That's why electricity flows so well through something like copper, or really any conductor. Then you got an insulator, and this insulator is actually more balanced, and these electrons there's no electron in the outer valence ring. These electrons they're chilling. They don't really want to leave. So if you were to try to conduct electricity through rubber or like through wood or something, it's not going to really try to do that. Makes sense? It's gonna resist the flow of electricity. So you guys know if you're let's say going to be working with electricity, sometimes you'll see those big rubber insulated gloves. Now you understand why, you know, let's say it's a lineman, the power company goes up on the pole and they're working with like thousands and thousands of volts. They're going to be all geared up in those big gloves. Even us, when we do work on hybrid, when we're disconnecting the high voltage disconnect, we're going to use those big gloves because the electricity really wants to leave that battery and it wants to actually go through our body and then go out your feet into the ground, right? Because the ground is where it can be balanced. You wear those big rubber gloves. Those rubber gloves are such a good insulator. It's not, you know, it's going to really protect you. It's going to be like, the electrons are saying, nah, we're not going to be able to break electrons off of whatever this one is. I don't know what AR is either. Okay, so there's a good conductor, there's a good insulator. Now, what the heck is a semiconductor? You guys ever heard of this? Semiconductor. That's when you get more into electronics. Semiconductor, you can pronounce it different ways. Semiconductor, depending on what we do, could be either. It's like if we do this thing, it can be an insulator. If we do that thing, it can be a conductor. So with electronics, it's kind of nice. We can actually use material like this for, let's say, a transistor, where we'll have all these semiconductor materials lined up, and if we send, let's say, a 12 volt positive into it, it'll actually make it so that current will flow through it. We can manipulate these to make them either conduct or insulate. You do either one. So as soon as you start talking about semiconductors, your brain should be going to electronics, computer chips. You know, these things like transistors either pass electricity or they don't pass electricity. And if it's flowing electricity, you know, it's a conductor, but if it's not flowing, it's an insulator, and we can change that based on other electricity. We can build these whole huge electronic circuits out of semiconductor material and have become a computer. Okay, cool. So this is just kind of going over what we talked about. The deficiency of electrons gives the atom an overall positive charge. So the positive ion, it's not balanced, it's looking for a change, okay? So what that means is it's actually exerting an attracting force on electrons, trying to pull one in. It's trying to pull one. Remember how the negative ion was trying to push one? If you have a negative ion, it's trying to push one to a positive ion, which is trying to pull one. Cool? And then these repelling and attracting forces cause the electron to actually be pushed off of one, off the negative, onto the positive, and the flow of electrons from atom to atom is called current flow. We got a new term right there. Current. Current can mean a number of things, but in electricity, when we talk about current, it's actually a measurement of the flow of the electrons. Now, when we're saying there's a little bit of current, it means there's a little bit of electrons leaving the negative, going to the positive, going from atom to atom, right? And that's why we call them ions. Cool, so if you have a good conductor and you have a situation where we have a positive charge and a negative charge, the amount of electrons that are flowing, like you could count them. If you were measuring current, you'd be like 1 electron, 2 electrons, 3 electrons, 4 electrons, 5. Okay, yeah, there's 5 amps. So current is measured in amps or amperes. So that's one of your first terms, which we're going to cover again. But when I think of current, you know what I think of? Water. You think of water. If you see like this little trickling stream, are you worried about that current? You're going to be like, no, don't cross that thing. It's scary. There's like just a little, come on, it's like a battling brook. But what if you see a river and the thing is like raging? It's got a lot more current, right? There's a lot more volume of water passing by. That'd be scary. You might get swept away in that one. So that's kind of what I see. Low current is just like a trickle of electrons. High current is like a, okay. High current can do a lot of work. Cool. And then we've talked a lot already about the conductors. So the free electrons, those are those singles that are out in the valence ring. That's that outlying electron that's ready to pop off, especially in an insulator. They're just loosely held by the nucleus. That's what's kind of interesting is, if you have the protons and the neutrons in the middle, then you have electrons that are close by. Those have, actually there's gravity there, which is crazy. And actually, I definitely don't understand, but even scientists are kind of like, there's gravity here, but electrons don't have a mass, or they change back and forth, okay? But if you think of like our sun, and then in the solar system, there's the planets that are going around, right? There's a lot more gravity on the larger mass. Well, those electrons that are way out there, they're almost outside of the reach of the gravitational pull. Make sense? So they're already kind of like ready to let go. Make sense? Now you kind of see why it's a good conductor. Those electrons way outside don't have a whole lot holding them there. Cool? And that's what it's saying. Atoms with fewer electrons in the valence ring are conductors. Now, if the material's made of atoms with 1 to 3 valence ring electrons are considered conductors. So if you look on the table of elements, all the ones with 1 to 3 electrons in the valence ring, those are conductors, and those will let go easily. The ones with fewer conductors are the best. The ones with fewer electrons are the best of all of the conductors. So, like for example, we use mostly copper. Copper is like our number 1. We do use other stuff too, but copper by default. If you were to just like go to work on the car and you were to work on a wire, it's probably going to be copper. There's some cases where it might be aluminum, but it's pretty rare. In houses, it's mostly going to be copper, but houses use aluminum a little bit more than cars do. Like aluminum's, if you wanted to run big wire from one side of the house to the other side of the house and it had to be fat because you need to run like, let's say, you guys been having a lot of power outages or just me?
Yeah. Mm-hmm.
All right, power outages, big pain in the butt. So let's say you want to run a super chingon generator. How's that sound? Am I right though? Am I right?
Yeah.
You want a generator that's going to run everything, including your heat and AC and all that type of stuff. Those generators will have to push like 240 volts at 100 amps. If you want to be able to move 100 amps, remember that's current flow, 100 amps of electricity, that's a lot. You need a big wire. If you want to buy big copper wire, you need big bucks. Like copper wire is double the cost of aluminum. So what you could do to save money is actually run a little bit bigger aluminum and buy the aluminum wire cheaper and then run that all the way to the generator and back up your whole thing and stuff like that. So we will occasionally use aluminum for like cost savings in houses, but on cars we generally don't. It'd be pretty rare. Copper's the go-to. A little expensive though. Okay, so here copper is a good one. One, right? Iron, 2, I believe. Aluminum, 2. Actually 3. 1, 2, 3. Cool. All still good conductors, but copper would be the better of those. And then we talked a lot about insulators already, so like any type of a plastic. So rubber's kind of a hard thing to define, but plastic, a rubber, so like for example, the electrons in the valence rings are bound much more tightly to the nucleus. The greater the number of valence ring electrons, the better the insulator. So you could look at several different examples of that. You could find what's the best insulator. And then if you guys are getting hot too, anybody want to be, Lark, you want to be in control of that thermostat? Just in case. If you're hot, let Lark know. Okay, semiconductors, like we said, materials that conduct more easily than insulators, but not as well as conductors. So they're kind of like
in between.
They're in between. Yeah, they're in between. And we didn't really care about those for a long time until we started to get more into electronics and we realized like, ooh, we could manipulate these and be like, hey, you're a semiconductor. So in this instance, act as an insulator. But if we do this, act as a conductor. Like if we provide electricity, we want you to conduct. It's kind of interesting. So again, used to make electronic. See, remember how we define the differences? We don't use semiconductors in electrical. We use semiconductors in electronic components, such as transistors, microchips. That's what I was saying. They can switch the material from a conductor to an insulator and back, but this is the key right here. What do you think that means? Like milliseconds. So when you guys send an email, do you expect it to take a while for the mailman, which could be a mail woman, to pick up your email and carry your email and put it in the car and then drive? Like it doesn't. Email's fast, right? Because all that stuff's computer based. Computers have to be very, very, very fast. Electronics have to be very, very fast. Semiconductors have to change from insulation to conducting very, very, very fast, or that's not useful to us. Make sense? And then semiconductor material can be used as a switch to control whether electrons flow through the semiconductor material or are stopped by adding or removing electrons. So if we were to just go to the very basics of computers, do you know what computers do? It's essentially like a whole bunch of on and off circuits. So if you wanted to talk computer language, computer speaks ones and zeros. Off 0, on 1. If you want to make a Morse code, you could say 1 0 off, 1. Exactly, and that means something. Your email is a string of on and off and on and off and on and off. Ones and zeros and ones and zeros and zeros and ones and zeros. Make sense? So that semiconductor can produce those on and off, which are zeros and ones, very, very, very rapidly. And we didn't exactly understand that. Like back in the day, we had Morse code, right? Boop, 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 boop. That was literally somebody making a contact, and that would be an on, that'd be like a 1, and then breaking the contact, that'd be like a 0. And they were doing that with their hand, and someone on the other line was like interpreting it and writing it down. So we had the idea, but we were using more like electricity and physical movement. Now we do the same thing, but we can do it so fast because of semiconductors, we can translate massive, massive amounts of information like in microseconds. So that really all started with semiconductors. Cool. And then, if you want them to move, we need a couple of things. For free electrons to move easily, they need two things. A complete pathway. Let's see. All right, that's the first thing. Which we call a circuit, by the way. You guys have heard of a circuit, right? So who's ever heard of an open circuit? That means there's no pathway. If I were to walk up to a wire and cut it, you know what I just made? I made an open circuit. Now you understand why it's an open circuit? There's no pathway for the electrons to flow. Cool. And a force that makes them want to move. Okay, so that's actually electromotive force, if you must know. And if you wanted to get super geeky, there's you guys know General Motors, government motors. You know, GM, right? GM car company. Did you know they also made locomotives? You know what a locomotive is? They pull the train, yeah. So the engine that pulls all the cars behind it, I worked on those. One of the main brands, GM made this brand, right? One of the main locomotive manufacturers is called EMD. It's General Motors Electromotive Division. You're like, electromotive, that sounds cool. So the force is electromotive force. It's like a motivational force for electrons to move. Here's a new term for you. You know what that is? Voltage. So we learned two new things. What is voltage? Voltage is the quantity, like the amount, the strength of the force, the electromotive force. And then amperage, or amps, is the quantity of the electrons flowing in the circuit. That's crazy, huh? So, like, if you were to think of, we had some fires, so let's just say that you're trying to fight a fire to save your cats or something, kittens. Yeah, like, I'm gonna save these cats. What type of hose do you want?
Full force.
Okay, what if you had a little hose and you turn on and there's like a little tiny needle jet of water?
That can make it so you can make pressure.
Yeah, so that's not going to do a whole lot of work, right? But what if you had like a really big hose? That sounds good. And you turn it on and there's like no pressure and the thing's like, blue. It's like this, like,
No more.
like that, right? So we need both of those to really do a lot of work. The lot of work in this case would be fight that fire, so you save them cats. Okay, otherwise you have to get dogs, which would probably be preferred if you ask me, but I'm just going to leave it at that. Okay, you're going to save these cats. You would like a lot of pressure, that's the force, and you'd like a lot of flow, that's the amps. So if you have a lot of volts and a lot of amps, that's going to be doing a lot of good work. Okay, in cars, we have a relatively fixed amount of electrical pressure. I'm going to say 12 volts. 12 volts in reality is more like, if your battery is fully charged, 12.6 volts. If the car is running, it's more like 13.5 volts. If your car is running and your alternator is really working hard, it might be 13.9 or 14, or it might only be 13.1, right? But we're in the range of 12-ish. Okay, and sometimes we'll call that the source voltage. So if you want to do work and your car makes 13.5 volts running, you can't increase the voltage that much. Cars don't make higher voltage on demand. You know how many volts the outlet in the building has, like to charge your phone? It ain't 12, I can tell you right now.
120, right?
Yeah, 120, exactly. So now you can see, like, you have 120 volts, that's going to have the potential to do a lot more work, but work is actually a combination of volts and amps. So on a car, when you go to start it, you know the sound it makes? Right, that one? That starter motor, that does a lot of work. It doesn't do a lot of work by having really high volts, though. It does a lot of work by having really high amps. Those can be like 300-400 amps.
And the amps is basically like what's it called? Oh my god, what the alternator would provide, right? Or the
Kind
starter.
of. So when you hear amps, when you hear like, oh, how many amps is the alternator? That's at maximum. How many amps can the alternator put out?
Oh, okay.
So when we're using a starter, the amps are leaving the battery
Oh,
and
so
they're
it's
going into the
providing
starter.
it.
Exactly.
Okay.
So we take electricity, we send it to the starter, and the starter goes no, and the engine goes like, okay, I'll get started. Here we go.
And so
Right.
amps are electricity
Current flow.
stored.
No,
No?
it's flow. So amps is current flow, right? So remember we were talking about the water flow? When you want to run a starter, you're talking like big fire hose, like there's a ton of amps because there's only 12 or 13 or 14 volts. We need a lot of amps to do that work. Whereas like what's kind of interesting is if we were to have a system that was higher volts, like let's say we had a 240 volt system, you could do the same amount of work with a lot less amps. So ultimately in automotive, we're looking at kind of like, what do we need the system to do? Do we need the starter to turn? Because we may need a whole lot of power. Power is volts times amps. We can either give it high volts or high amps. In automotive, it's not going to be high volts. We only have 12 volt systems. It's going to be high amps. That's why your battery cable is big. Lot of amps, lot of water flow. It's like a big water hose. We need the amps to go through that sucker. Now think about, there you are trying to save those cats. You know, they're in there. You're like, I'm going to save you. And then you got the fire hose like this. But let's just say you're stepping on the fire hose and the fire hose like this, but then it gets drawn down to like, it's kind of kinked. What do you think? What do you think is going to be, what's going to happen to your water flow?
It's gonna be low.
Yeah, it's going to be low. You guys have not, you have siblings or what?
Yeah.
With brothers and sisters and stuff, and you kink the hose and you're like, hey, go look at the end of the hose, see if there's something in there. And they're like, there's nothing coming out, you know, and then what do? Unkink it, right? So the kink in the hose is going to reduce the amps, right? That kind of sucks. That's resistance right there. Resistance to flow. Resistance to flow is like the kink in the hose. And that's ohms. Okay, so I promise you we're going to cover those again, but I'm hitting you several times today.
So when you're saying last little while ago, the open circuit.
Yeah?
So when you get a code that says circuit open,
Yeah.
was that?
I can give you very, very technical, which you will not be ready for,
Okay.
or I'll give you basic. Your computer monitors that circuit, and if the computer says there's an open circuit, generally there's an open circuit.
That's the code I get for my airbag. It's an open circuit.
Exactly. Where's the open circuit though? The computer can't tell. Makes sense? So the computer, there's a couple tricks the computer can do. Voltage divider circuit, it can measure amps.
Oh.
It could do some things. A lot of times it'll do like the voltage divider will use two different resistors, but it can predict there's an open in that wire out there. But where? I don't know. It could be right at the computer. It could be a little ways down.
Swap 2.
Exactly, but the squib, it's the squib in the airbag circuit, that's a whole circuit. So the computer puts stuff out on a wire, and it goes through the squib, and then it comes back, and it knows there's an open somewhere out there. The problem is, and this is kind of the essence of what you guys are trying to learn, when there's a problem in the circuit, your job is to find out where the problem in the circuit is. Right off the bat, when you're saying open circuit, that means there's excessive resistance. The most resistance you can have is an open, right? So when we said we kink the hose, that's a little bit of resistance, right? You're not going to have a lot of flow. Well, what if I cut the hose in half and I threw one over there and I threw it over there? You know you don't have no pressure in there. You have no water flow coming through the hose where you want it at the nozzle. The question is, where is the open though? So in that example, let me switch it and make it a headlight, okay? Because a headlight's easier to visualize. Your headlight doesn't work. It could be the bulb, right? Which would mean the opens in the actual filament right there. Cool. And that, you plug a new bulb in, it'll work. That's not diagnosis. You're just jamming parts in there to see if it fixes it. And that's fine, because like the bulbs fail all the time. Parts cannon. See, you learned to turn last time, huh? Now you understand. A parts can is where you just jam parts on there. If it fixes it, cool. And as a DIY person, you could probably do that. But as a professional, what are you going to tell the customer? You'd be like, hey, I didn't really know what was wrong, so I tried this part. You got to pay for the part. You got to pay for my labor. And they're going to be like, I didn't get anything fixed. I don't want to pay you. And then, you're going to have to try to fight. So we're not training you to be like that. We're training you to be able to really troubleshoot it. So if it's a headlight and it's not working, we can actually measure voltage at different points along the circuit and be like, oh, the open is before the bulb or before the switch or after the bulb, it's on the ground side, right? We can perform measurements and determine where is the open circuit and then make a recommendation on what needs to be replaced. Cool, that's diagnosis. Same concept for your airbag. The problem I'll tell you with an airbag is like with a light, you know, we're doing various testing. If you wanted to measure resistance on a light bulb, you can. And if you measure resistance and it's open, you're like, okay, there's an open right there. But with an airbag, if you try to measure resistance, it uses a 9-volt battery in your meter. You could actually charge the squib, and you know what happens if the squib gets some current going through it? Airbag deployment. In your face, break your nose, blow the windshield out. It'll total the car.
No, is it expensive to get it checked, or is it like?
It's a different technique. So if we have time at the very end, we'll get into airbags a little bit, but generally, SRS, the supplemental restraint system, is like electrical too.
So it's,
But I'll give you some advice. Generally, the way that you proceed on those is you could take the airbag out, disconnect it, set it down. And then you're back to basic electrical. Measure this wire, measure this wire. If this wire is good and this wire is good, you're now between the airbag itself, the squib is inside the airbag. It's like the bulb, right?
yeah.
Could be the bulb. Or it could technically be the computer, but that's kind of rare. The more professional way is you can't measure the resistance of your airbag squib, but in service info it'll say, oh, this is like a 10 ohm airbag squib. You could actually take the airbag out and put a 10 ohm resistor in there, and if it fixes the code, you know that it's the airbag. If it doesn't fix the code, you know it's something else. So
So should I go to a auto shop instead?
I think you should just wait till you get the skills, and then you'll diagnose it. I bet you by the end of the class I think you'll be able to do it.
So it's okay to.
Run it. It just means your airbags don't work right now. Buckle up. Cars didn't have no airbag for a long time. It's true. All right, so you guys feel like kind of okay on the charge difference, right? Okay, I think we're good there.
Dad thing, you fill the dashboard with burger wrappers.
All right, burger wrapper. We're moving on. Now look. The larger the charge between the negative and the positive terminal, the more strongly the positive terminal attracts the negative terminal and repels free electrons. Hold up. What I'm saying is, remember this thing? Over here is the negative. The more electrons are in here and the less electrons are in here, the more the differential. See what I'm saying? The bigger the difference. The more it's like these electrons either kind of want to get over there or like they really want to get over there. So if you have a fully charged battery, what that means is this negative side is packed with electrons, which increases the voltage difference. So when we say voltage, remember that's the pressure. The pressure difference has to do with the difference between positive and negative, okay? And normally in my mind, I'm thinking they're going positive, negative, and we'll switch back over to that when we get a little more practical. But to be true to the science, we'll stick with electron theory. The more negative electrons are here, the more extreme the imbalance is, that's higher voltage difference, right? So when you say voltage, you're like, well, what is voltage? Well, if I'm telling you this battery is kind of discharged, it could be 11 volts. That's going to push with 11 volts of power. But if I fully charge this on the charger and it's 12.6, it's going to be pushing with like 12.6 volts of power. Think of it as PSI. 11 psi, 12.6 psi, more pressure, right? That's really how this battery is going to work. So if your battery's discharged and you get in to start the car, how's your starter sound? Stop doing that. Remember how it sounded, sha-na-na-na-na-na, right? If it's kind of discharged, it's like sha-na-na-na-na-na. You know this isn't good. Your battery's dying. Now your battery could be discharged, but your battery could also be defective, right? So we're going to go into batteries, and when a battery is no good, it's hard to have that high voltage. It's just going to have like a surface charge. It's not really going to be able to provide a lot of cold cranking amps, right? Now you understand cold cranking amps are the amount of current flow it can provide, right? So a good battery that's charged, 12.6 volts, that provides a larger charge difference, which means more electromotive force, more voltage. Cool? Kind of getting it a little bit? Okay, and then when we get into 90-something% of circuits on the car, we're just talking DC. Okay, it's much easier for me to explain DC. I think it's easier for you to understand DC. So we're going to focus on DC. But then we're going to have to switch over to AC, and I think you'll pretty much get it. So on the car, passenger vehicles, direct current. So that's DC. There's a lot of terms today. So direct current is DC. Direct current essentially means electrons flow in one direction only. So that means in this battery, what's the one direction? Negative to positive. Negative to positive. They don't ever be like, you know what, today I'm gonna, go this way. Don't work that way. This is direct current. Now the house on the wall, not the case. I'm just talking about DC for now, is direct current. Battery stuff's always gonna be DC. So in the vehicle, you turn on the lights, the electrons are leaving the battery, they're going to the light. They're actually coming back to the battery, but you just picture it leaving the battery, going through the light. It's never like, let me leave the battery and then go right back to where it came from. Let me leave the negative and go back to the negative. No. Direct current, it goes from negative to positive. Makes sense, period. And so again, here's your verification. Electromotive force, which is measured in volts. So we could, if you want, call it electromotive force. Be like, oh, hey, Gregory, you working on that car? How much electromotive force is available at the headlight connector? You'd be like, what? What we're really going to say is, hey, what's the voltage? And you'll be like, 12.6. We're like, okay, cool, right? But we say it like that because that's how we measure it. It's the same really as electromotive force. We're basically saying how much force does it have, but we measure it in volts, so we say how many volts does it have. Make sense? Mm-hmm.
I lived in an electrical car.
Yeah.
The voltage will always be 12. Unless you're doing...
Okay, I'll bite. I thought about rejecting it, but I'm going to bite. With electrical systems, which is where we're starting, bulbs, power window motors, locks, a fuel pump, something like that, we're dealing with source voltage, 12.6 on fully charged. If you're testing it running, maybe the 13.1, 13.4, 13.5, around there, yes. However, if we're dealing with, remember those subjects, how we get into transmissions and engine performance and emissions controls? Those use sensors? No. A lot of times those sensors will function on a 5-volt system. 5 volts is it's just a little bit different. It's kind of nice because we can take our source voltage, we can regulate it super clean and tight and make exactly 5 volts. So when I say 12 volts, I just explained it could be 12.5, it could be 12.6, it could be 13.1. It's a range, right? Your sensors need a very steady, clean voltage. Whether your battery's kind of dead, whether your car's running, whether you're going uphill, whether, they need a very clean voltage. Whether your alternator belt slips a tiny bit. So we drop those down to 5 and we make it a 5.0 flat, clean. And then that can give us an accurate sensor reading. So sensor's gonna be on 5, but wait, there's more. Sometimes power steering systems can be bumped up higher, 24, 48 volts. A lot of tractor trailers run 24 volts. If you get into, let's say, a Jeep Wrangler, say it's a 2018 to current, and it's got the e-torque assist, that whole system is 12 volts. However, it's got a belt alternator starter system on it that makes a 48 volt, and that 48 volt goes to a lithium-ion battery. And that lithium-ion battery can store the electricity so that when you go to do a start-stop on that, it'll actually use the 48-volt system to turn that belt alternator starter and boom, start the engine real quick without you hearing the starter, right? But then while you're driving, it's making 48 volts and shoving it in the battery. So there's all sorts of different stuff going on in cars now. But back in the day, 12 volts, have a nice day. 12 volts, and then kind of when I went to school, they're like, hey, you know, on some cars, they're hybrid, and it might be 36 volts, it might be 48 volts. Then in a full-blown hybrid, they may be 200 something. Some cars have gone to like the 400 volt architecture. Some have gone to 800, which is very rare, but some have. So the voltage is all over the place. The good news is everything we're talking about right here is the same. It operates the same, you calculate it the same, you measure it the same, other than 12 volts. You ready for this? It doesn't do anything to you, so don't even worry. 12 volts, yay, no problem.
But is it really passing through you though?
It doesn't have enough voltage to send substantial amperage through.
Okay, alright.
You know, there might be like some of these things you'll see on social media about grounding. Oh, grounding fixed my arthritis and all that type of stuff. I don't know. I don't know. I really
Copper
don't.
stuff?
Yeah, sure, absolutely.
Copper socks?
Sure. Okay, but 12 volts, really not dangerous. Now, if you take your wrench and you lay it across this battery, sparks are gonna fly. You can be welding. But for your personal safety, you don't ever have to worry about, oh, I touched the positive and I touched the chassis and not gonna happen. However, 48 volts starts to get a little sketchier. So those systems are gonna not be, they're not gonna look the same. That's like a medium voltage. They're gonna put that in blue. So if you see a bunch of blue wiring and this weird stuff, you'll be like, maybe I shouldn't just go probing that. Make sense? Now, to keep you safe, the way the whole world works is very interesting. If you were in a jungle and you saw a snake and it had like orange rings on it, doesn't that kind of sketch you out? You're like, whoa, why is that snake so colorful? Probably means it's got some venom in there. Okay, if you see orange wires, that's a snake with venom. That venom's like rattlesnake venom.
Should have made the orange people like snake feet.
Yeah, they should have, I agree. But they're like, you know what? Orange. So if you see orange, starting out with this, if you see orange, that has high electromotive force. Like maybe 180, 200, 240, 256, you know, depending on the model. That's high voltage. They make it orange so that you as a technician don't be like, oh, let me put my meter right there and test that. That 200 something volts is enough absolutely to go, there's enough force, right? Now that you understand voltage, there's enough electromotive force to push those electrons into your arm, through your heart, out the other arm. You can make lightning, bah, you know, and you could also make dead, like that. It could kill you, for real, not even joking around. Don't be scared, because there's massive safety protocols that we'll cover, but on a hybrid or electric vehicle, those orange cables, they're orange because they want you to know if you do the wrong thing right there, you can be, how would you say? Fried, I like that. You could be fried. And if I wanted to make you very safe, you could go on to the YouTube and you can find like some guy in India on the train and he reaches up and he touches the cable. You know, on some of those small, like, not the diesel, like I used to work on the diesel electric stuff, but on those little trains, like the trolleys that go through the city, you know, sometimes there's a third rail in the middle, or other times there's like a third wire on the top and it has like an arm. That's where the high voltage is, and that's what powers the electric motors. Well, this guy's all crazy and stuff, and he goes up and he touches it, and what do you think happens?
Where?
It made almost that same sound. You can literally hear it go, it just dong dong, and then he's on fire. I mean, so it will kill you. There's no two ways about it. But in a car, luckily for you, we're really working with 12 volt system. If you're going to go beyond the 12 volt system, no problem. We got a class for that. If you want to take the hybrid EV class, it's a great idea. A couple of you are taking it now. You'll know about it. Right? Who's taking it? So you're going to know some
Are they
stuff.
gonna have it next fall? No.
I don't know.
Next
They usually only run that once a year. Most students don't want to take hybrid EV. They're like, I hate those cars. But I'm telling you. A lot of people hear this story about the guy getting fried and he looks like a hot dog that was left in the microwave too long, and they're like, I'm not working on it. No problem. I respect that. However, I'm going to work on it and I'm going to charge more because there's less of me, and a lot of people who are like, forget that, I'll work on the 12 volts, but I won't work on the 200 something. So it makes you worth more money if you can do that. Make sense? So just think about it.
But
And
higher
it's
risk.
Higher risk, but honestly, with the right training, if you have a good understanding, I'm not even worried about it. Like I really know what I've got. I know where I have to wear gloves. But generally, I'm only wearing gloves for a small part, and then I'll measure, I'll verify the voltage is 0, and then the gloves are off, and I'm working on normal stuff. I just have to make sure I get myself to that point, and then I'm safe. It's not, it seems scary, but if you take the class, you'll understand it. But now you'll understand the science of it. The higher voltage has higher electromotive force, and that has enough pressure to push the electrons through your body, make your eyes be like Raiden and things like that. Okay, so now we're going to get some of those same terms. Electrical resistance, remember that one? That's the resistance to flow. That's like the hose that's kind of like kinked. Cool. Measured in ohms. I'm going to not write on this projector screen today, but I'm definitely was just thinking like, let me draw the ohms thing, and then I'll get it off. So ohms looks like the omega symbol. We'll be looking at it a little bit later. So the electrical resistance, ohms, affects the current flow in a circuit. Remember, I already told you about the fire hose. So if you go to save those cats and you turn on the fire hose and the water's like, you're like, oh no, I don't have a lot of pressure right there. Like those people in the Pacific Palisades. That's a big problem with what happened, right? The firefighters hooked up their hose, they turned it on, and it was like hard to fight the fire when we don't have water pressure at the fire hydrants. Makes sense? So that's a problem. Now we would need somebody to go in and troubleshoot it, but electrically it's slightly different, but it's still the same visual cue, right? If the light bulb needs a certain amount of electrical current to glow, but it's not getting enough electrical current, it's either not going to glow at all or it's going to be kind of dim, kind of like the firefighter that turned the thing on. It was like there's a little water, but not enough to fight the fire, right? Somebody's got to troubleshoot the circuit. If you were to picture that firefighter, can you imagine if you had that pipe and it was like packed full of rust? Don't you think that could cause it? Imagine there's like a whole bunch of rust in the pipe. That would be resistance. Cool? So that resistance is, we can measure that. We can measure it in amps, right? So if we have symptoms that lead you to believe there's excessive resistance in the circuit, cool, we can measure that. Nice. You could put your meter on there and be like, it does or it doesn't. And that's part of the reason I like automotive, is it's not so much a matter of opinion. If you wanted to tell me your opinion, I can tell you my opinion, and who cares? It's sort of like everybody, you do you, dude. Everybody's opinion. It's your truth. I don't like that. I want the matter of fact. If you think it has excessive electrical resistance, I know. We can measure it. Then you can be like, well, I think it does. And I could say, like, I measured it and it doesn't. As a matter of fact. Make sense? So if you picture it like that, this isn't really artsy where you get to, you're right in your own way type of thing. It's got excessive or it doesn't got excessive. Period. You don't get to just run with it. You measure it. And if you measure it and it's excessive, then it's excessive. And if you measure it and it isn't, then it isn't. See how I think that's just so nice. But when we diagnose it, that's how we do it. So you call the customer, you don't say, well, I think there's excessive resistance in that circuit, because what you really should call and say, I measured there's excessive resistance in that circuit and it is 100 ohms. And that's too much. And you're like, okay, well, as a matter of fact, great. So what's the fix? Oh, you need to replace the wiring harness. Oh, you need to replace the switch, right? The something. So we're measuring, and you could say it in another way. We're proving the part is bad. Makes sense? You're not saying, well, it's my opinion that you should replace that light switch. You'd say, I measured it. This is the measurement. That light switch is defective, period. See? Love it. Gotta have it. Okay, so that's how we measure the resistance. But there are some factors, okay? So resistance varies naturally. The type of the material, so if it's a good conductor, it should have low resistance. That should be really good for a lot of current flow, right? Like remember copper? Copper is going to have low resistance. You want to send electrons through your body actually has kind of higher resistance. You can measure your body's resistance if you want. You could take one lead and another lead and put the meter on ohms, and you could go ahead and measure your own internal resistance. It varies, depends. You all are just slightly different. But it's not, you're not a good conductor, so you don't have low resistance. You have kind of high resistance. You could drive your Jeep. We'll start with that. Okay, another thing, the length of the conductor. So this is kind of the thing. If you had like a kind of a short wire, you know, it's not that hard for the electrons to go through. But if you had a really, really long wire, actually the resistance builds up over the feet and feet and feet. So if you had a great copper wire, it was really cool. And then let's say you were, here we're in San Jacinto. You wanted to run power to Temecula. You take that little wire and you run it all the way to Temecula, 30, 40 miles from here. That resistance is going to be, it's going to add up over feet and miles. Make sense? So let's pause right there for just a moment. If I'm telling you the longer the conductor, the more resistance there is, how is it that we send power on these power lines, all those, we send it thousands of miles? How do we do that?
Because every certain length, there's a what's it called? Like on each pole.
I like your thought. I'm picking up a little bit. You said a word called transformer. Let me explain what a transformer does. A transformer steps up or steps down voltage. So if you had 12 volts and you tried to run your 12 volt wire to Temecula, it ain't happening. 12 volts is not enough electromotive force to push 40 miles of wire. It's not going to happen. Now, if you had a really big wire, actually maybe it would, but that's kind of what I'm saying. There's this balance of like the size, the type. Let's say we're copper, but right here there's length and diameter. The bigger diameter, the less resistance, but still like 40 miles is a long way for a wire to go with 12 volts. So what we do, we take the transformer and we'll step it up. We'll go into kilovolts. We'll do thousands of volts, 20,000 volts. That's so much electrical force, so much pressure. Sure, it'll run those. You know what they call those a lot of times? Like a high tension line. Like that's why those aren't, not the basic power poles. I'm talking about the big metal, big old things that are really high up in the air and they don't really let you go around and play around those. Those are like 20,000 volts. You can go hundreds of miles with that. Why though? You understand why? Why can that go so far? Those cables aren't huge, by the way. They're really not that big. Why is it able to go hundreds of miles? Tell it back to me.
Alternating current.
Good idea, but we could do it with DC too, if we wanted. It has to do with that transformer thing. We increased, what did we increase? The voltage, exactly, the voltage. If you bring the voltage up, you can push through some stuff, okay? So when we're talking about this, I want to make a point. All this affects the resistance. And on a car, this is really, really, really critical because we're only dealing with like 12 volts, right? So like a little corrosion in a car with 12 volts becomes a bigger problem. Actually, if you were to have a 120 volt system, it would be less of a problem. That's kind of crazy, huh? But it's true. And then also the temperature of the conductor. So all these affect the resistance. Type, length, diameter, temperature. For example, if you had, let's say, a solenoid. So it's early to get into solenoids, but we'll go with it. A solenoid takes the 12 volts, it goes through a load, which is the solenoid, and it goes out. And when you send the current flow through the solenoid, it makes it magnetized. We could do work with that. If you were trying to test a solenoid, you would actually test the resistance, but it'll give you a range. And it may say, you know, maybe 8 to 10 ohms. And you're like, why 8 to 10? Why not just 10? Well, that's because they know if it's kind of like cold outside, it might be 8, but if it's kind of hot outside, it might be 10. And then if you get it really hot, it might go over 10. So keep this in mind when you're doing these measurements. The resistance measurement is always going to vary a little bit based on these factors. So if it gives you a range, you just want it to be in the range. And if it's slightly out of range, you may take a step back and say, is the resistance a little high because it's a little extra hot today? Or because maybe you're working on it and it's a transmission solenoid and the transmission fluid temperature is really hot, so the solenoid's hot, the resistance can be a little higher than normal. A lot of times when they give you the specification, it's at room temperature. And sometimes we don't get room temperature here, you know, so there's a little leeway there. Okay, and then the next thing is a resistor. So the resistor is a component. Resistance is like a electrical measurement and kind of like a concept, but a resistor is a part. It's a component. It's a component designed to extract energy from the current flow by forcing it through a restriction in the circuit. What? So let's just say you have the battery. The battery is your source of voltage, right? This is your source. Sometimes when we're measuring voltage, some people will call it source. Does that have source? And you're like, does it have what? Source voltage. This is the source. Source voltage 12.6. Depending, remember, even if it's running or not. Does that have source voltage? Well, I don't know. How would you know what the source voltage is? What exactly? I saw that motion. Put your meter on here, measure it. If this is 12.6, then you go out to the headlight and you measure 12.6. That's amazing. That headlight has everything it needs to work. Good. But what we do, we send this source voltage through a wire. The wire should have little to no resistance. And if it has little to no resistance and it has a clear pathway, here's a new term for you, that's called like continuity. I'm like, what? Another term? Okay, continuity means there's a good path for the electrons. That's all it means. Continuity and resistance are the same, but it's like two sides of the same coin. When you're measuring the resistance to electrical flow, you call it resistance. When you're looking at it on this side, like how easy is it to flow, you a lot of times call that continuity. Is there continuity between this point and the bulb, right? That means, is there a path? How do we measure it? You put the meter on ohms, which measures resistance. When you're measuring resistance, you're measuring for a low resistance number, which is kind of like measuring good continuity. See how those could be kind of the same, but talking about it a little different? A lot of times DIY people are really all about continuity. You put the meter on resistance, you push a little button, and it's called a continuity test. And if you put on this end of the wire and this end of the wire and it's got good continuity, you know what it does? Beep. You know, you're right, that's got continuity. And then you'd be like, let me go the other wire. Beep, that's got continuity. That's a good test. That's fine. The way that we tend to look at it, though, from automotive is like, is there excessive resistance, yes or no? And if it goes beep, you'd be like, all right, there's not excessive resistance. But a lot of times we won't do a continuity test on the meter. You can, if your meter can do that, make it beep if you want, no problem. A lot of times what we'll do is we'll actually measure it and we'll look at it. And if you had 0.2 ohms, that wire is nice. That wire has low resistance. The other side of the coin, that wire has good continuity. This side of the coin, that wire has low resistance. Make sense? It's two different ways, kind of say the same thing. So I've gotten in debates with people, which I don't normally do, but especially in other industries, right? I did some testing, I showed on YouTube, and I said, you know, we're testing here for low resistance, and the guy's like, you're not testing resistance, you're testing continuity. That's continuity. Why don't you just say continuity? Sort of like, say continuity if you want. It's just typically in automotive, you'll rarely hear the term continuity. Okay, just saying. So we test the resistance. Boom, it's good. We test. Then we go to the bulb. We're going to use the bulb as a lot of our examples. Do you think the bulb should have low resistance? Because if the wire has low resistance, it helps the electrical current flow. Then what's the purpose of the bulb then? You know,
To hold?
we want the bulb to have resistance, but we need it to have the correct amount. So if your bulb resistance is 4 ohms, basically what's going to happen is the wire is going to have little resistance. It's going to go to the bulb, which has the little filament in there, right? The tungsten wire that's wound. That's a resistor on purpose. That resistor is supposed to be there. And when the current goes through that resistor, do you know what happens? It makes a lot of heat. and the heat makes it glow. And then sometimes you have halogen, we have, you know, different gas sometimes in there. But if it's just your basic tail light, it's just literally the electrons flowing through that little element in there, the filament will glow, and that's why your bulb works. Cool? And then we have to have good continuity or low resistance back to the battery, right? So if you have a good pathway to the bulb and the bulb resistance is correct, and then you have a good pathway out of the bulb, electrons will march their way right into that bulb, go through that filament, make it glow bright, and then go right back to the technically I'm going to say to the ground, but in science it goes right back to the positive of the battery technically. Okay, it's just weird. Cool. So the resistor is a component that's designed to extract energy. How did the bulb extract energy? What did the bulb give us in exchange for this energy? What work did it provide? Light. So let there be light. No problem. We give that bulb the voltage it needs. If the bulb has the correct resistance, the work is the light. What about Mason? When Mason gets his e-bike, how are we going to make Mason be able to get here without the bus? We're going to send current out of the battery. It's going to go to the motor. The motor is, in a way, it's a resistor too. What's the motor going to give us? Like rotation. It's going to give us rotation. Now, if you were to break it down internally, it really gives you like attraction, attract and repel magnetic field. So magnetism is actually the work on the motor. Cool. What about, you guys are nice and warm and toasty now, that space heater. Remember, you plug the space heater in, and you turn it on, and what does the space heater give you in exchange for that electricity you give it?
Heat.
Heat, exactly. So see, like, we make electricity do work. We do that generally through a resistor. So there's going to be some sort of resistor, but what I'd like to call it now is yet another term, the load of the circuit. The load is the worker. The load does the work. The bulb is the load. The motor is the load. The space heater is the load in the circuit, right? So we want to have a wire to get the current to the load, and then we want the load to take all the voltage to do all the work it's supposed to do, and then back. Now here's the problem. We talked about this right here. If we have excessive resistance, maybe because the conductor's too hot, or more realistically, maybe because the conductor's corroded. You guys know what corrosion is, right? Oxidation, green, rusty, corrosion. That adds resistance, right? And if that adds resistance, that's going to decrease the amount of current. And guess what? Remember the load? Now the load gets less current. So if it's a bulb, what's the bulb going to do now? It's going to be dim, exactly. Boom, you got it. What if it's Mason's motor? Mason's going to be late. Mason's going to be late because it's going to be slow, exactly. If it's your starter motor of the car and there's a lot of resistance on the battery terminal, like that corrosion and stuff, you go to crank it, it might be right?
Bad cold.
Exactly. Yeah, something like that. So that's kind of the relationship, at least to start. Resistance is a good thing when it's in the right place at the load. Resistance that's unwanted causes problems in our circuits. So what do? We hunt it down, but with the meter. We don't say like, my opinion is you need a new battery cable, and I'm right and it's my truth, and I walk on my own truth. It's my truth. Makes sense? Like, okay, let me know how that holds up in court. Misdiagnose it. So here you go. Now we got some visuals. You ready? You've heard all the basics. Now, here I am. I'm pushing on these electrons. Make sense? Electromotive force. How do we measure that? I'm pushing. Yeah, exactly. Voltage is the amount of pressure. How hard I'm pushing is the amount of pressure. We measure that in voltage. Cool? We can do that with our meter. And then, you see the electrons trying to move? They're trying to move through the wire. Resistance, what's the resistance doing?
Push it back.
Yeah, it's like the amount of opposition to current flow which is, it's inherent. That means like there's always some resistance, but we want it to be little. So if you measure a wire, you're probably not going to get 0.0 ohms. If you do, I guarantee you won't get 0.0000000. Somewhere there is resistance in the circuit. We just don't want it to be excessive. We have specs for that. So here it is, the resistance is kind of like trying to slow it down, right? That firefighter went ahead and they turned that hose on and there was excessive resistance in the circuit and there wasn't that many electrons flowing out and the house burnt. Make sense? Okay, now it's slightly different in water because actually, as far as we know, probably what happened with that, there was too many loads on that. There's too many people trying to draw from those pipes and like, the size of a pipe can only allow so much water, okay? So it's slightly different, but I'm still going to use it as a visual, okay? And then, what's this? The current, the flow of electrons in a wire. So current's tough. You can't really see the current. Make sense? So do you want to know how you'd see the current? You'd have to count the number of electrons. That's what your meter does when you measure current. Your meter is actually literally counting electrons. The way we measure resistance, it's kind of easy. You put it on one end and the other end, and you put it on ohms, and you see how hard it is for the electrons to go through. You could do that easily. The way you measure voltage, a couple different ways. You could put your negative lead on the battery ground or on the chassis, and then you put the positive lead here, and you'll get a pressure reading. And then you put it here, and you get a pressure reading. So if there was a kink in the hose right here, you could measure voltage here and it'd be 12.6, and you could measure voltage here and it might only be 5. That's because there's a kink in the hose, right? So the voltage measurement, you can track it down. There's another way to measure voltage. You could take both of your leads, put one here and put one here, and then basically what it's going to measure is the pressure differential from the red lead to the black lead. But we call that something slightly different. That's voltage drop. Right? So just the first time you're going to hear it, you're not really going to understand it right now. We're going to cover that again and again. You'll see it's going to take you weeks to really understand this. Right, so there's the way we measure voltage, there's the way we measure resistance. The way you measure amperage is totally different. You ready? You have to actually open the circuit up, and you have to send it into your meter, and then send it out of your meter. So you literally have to find a spot where you can disconnect this wire and reroute it through your meter, so your meter can count the electrons. 1, 2, 3, 4, 5. Pretty much that's what it does. Okay. And then it goes out. It has to go through your meter. If you do that wrong, you'll blow the fuse in your meter. Somebody is going to blow the fuse in their meter. I'm going to tell you right now. That happens every time. However, there's one other way, and it's not real precise. It's called an inductive clamp, and you can just clamp it around the wire, and the amount of electrons that are going through make a certain magnetic field, and that tester can get it fairly close to how many amps are going through. That's another nice tool. But in automotive, a lot of times we don't really use that so much. We're using it more, but back in the day we never used it. Now we're kind of using it. So there's 3 different measurements we just talked about. Mainly, you're trying to focus on understanding voltage, amperage or current flow, and resistance for now. So we got a few more different ways to look at the same thing. So there's your voltage. Remember, voltage is what?
Pressure.
Electrical pressure. How hard is it pushing? How hard is it pushing? You got to get the, for sure, like today's basic, but you got to get these. Electrical pressure. How's voltage created? It's created by a difference in electrical charge between 2 points. So now if we go way back to the science, remember we were looking at the excessive buildup of electrons and the deficiency of electrons. So if you have a whole lot of electrons over here and not a lot of electrons over here, that's going to make a certain amount of force, remember? So if you have a ton of negative and not a lot of negative, that's going to be a higher voltage, which sometimes we'll also call potential. So there's a lot of terms. It can be a little bit confusing, but if you were to measure 12.6 volts, they're saying like that's a difference in voltage, which means that's a potential for work. Makes sense? There's potential there. It's a lot of potential. You got 12.6 volts, it's a lot of potential. If you got a battery and it's at 2 volts, you think you're going to get that battery to do a lot of work? That battery doesn't have as much potential. So sometimes we call it potential, okay? Sometimes the way I'll visualize that is let's say that you have like a boulder. There you have this rock. It's a bowling ball. How about a bowling ball? You got a bowling ball. If the bowling ball's at the bottom of the hill, it doesn't really have a lot of potential to do much. It's just going to be sitting there. What if you were to roll that bowling ball all the way up to the top of the hill? Now that bowling ball has the potential to do something. Knock down a bunch of pins, run into Mason on his way in on his e-bike, be entertaining, you know. Bang into the side of a Jeep potentially, right? It has a lot more potential for work because it's at the top of the hill. Make sense? So sometimes when we talk about voltage, you'll hear it described as potential too. It's just the way it is.
Big bone, not the big bone ball. It's
Big ball in ball. Well, it might be bouncing too. It was a big hill because it had a lot of potential.
So it's like a rock.
And if it was a small hill, it has the potential to put a little dent. But if it's a big hill, it has the potential to cave the whole side of that door in. I wish nothing bad upon you and your Jeep. I'm just trying to make you understand.
I can legally drive without the horse.
That's true. I would recommend having the doors on in this case, especially if it's the driver's side.
Have you seen the video where like how much of a car can you take off while it still functions as a car?
Oh, there's probably a lot. You'd probably take a lot off.
Under Cal, you can take off your fenders, you can technically take off your hood, you can take off your doors. you
All
can
right,
take
let's
off
not
your
push
brakes.
the limit here. Automotive battery has approximately 12.6 volts between the terminals. That's on fully charged. Okay, so that would be like your measurements right there. Boom, 12.6 volts would be fully charged. I don't know what this one is. We can check it later.
That's it.
Make sense, Ronnie?
What battery did that come out of?
This is a motorcycle battery. It's probably my guess. Yeah, motorcycle ATV. They have different terminals. You notice it has kind of like these weird little screws. That's a motorcycle or ATV for sure.
That looks like a power wheel kind of battery.
It could be, yeah. Same type of idea. Okay, and then your current, remember, and it's kind of frustrating because like normal, there's always different terminologies, right? We just talked about potential. Current flow, amps, amperes, your pick. We'll call it current for now. Remember, it's the flow. How many electrons? Right? 1, 2, 3. How many are flowing through in a given moment? You know, like this is single file. That wouldn't really be all that many electrons. But if you had 4 wide, that would be more electrons, right? That's basically your current flow. So, however, current flows only if there's a complete path for electron flow. And it has to be between a source of higher voltage and lower voltage. So, now I'm going to add something. I don't like these terms because I think it's already kind of cloudy to understand this. I think this makes it worse. But however, there's a lot of good material out there where the people use these terms, and there's a lot of technicians in the shop every day that use these terms. So I'm going to comply, even though I don't want to. Power and ground. Okay. From a pure standpoint, power is a formula for work. It's volts times amps. So when somebody says, does it have power, and they're checking voltage, voltage doesn't measure power. Voltage measures voltage. Voltage measures potential. Voltage measures electromotive force. Voltage itself doesn't measure power, right? Because power equals volts times amps. And if you have it on volts, it isn't measuring amps, so it's not power. Whew, I feel better. Now that I've gotten that squared away, I'm fine because when someone says power, what they more mean is voltage. So if someone says, oh, check for power, they mean voltage. Yeah. They'll be like, check to see if that headlight doesn't work, check to see if it has power. Okay? Bring your meter over, put it on voltage, think to yourself, why did I say power when I'm checking voltage? These things in my mind. Then you check the voltage, but that's fine. It's just a term. Okay? Now, what is power and what is ground? Anything on the positive side, we could call power, if you will. Okay? Does it have power? So, you guys have little things to charge your phones in your car, cigarette lighters,
Yeah.
these things. Does it have power? If it doesn't work, like you plug it in and your phone doesn't charge, and be like, first thing, does it have power? Cool. Technically, you're going to check to see if it has voltage. If it has voltage, and you're like, oh, that's weird, Then the next thing you should check if it has ground. So voltage would be reading like a source, 12.6. Ground would be reading a like 0. Making sure that it has both of those. If it has 12 volts and it has ground, it's a problem with your phone charger then. Makes sense? That's how you diagnose, is it your charger or is it the outlet? Make sense? So when we say power and ground, what we really mean, if you look right here, this is the circuit. 12 volts, okay, now I'm switching away from electron theory because I'm telling you, electron theory is the fact, I know that, but all the wiring diagrams are drawn like this, okay? If you try to do it backwards, I'm gonna freak out. All right? They're all like this, okay? 12 volts comes out, it goes to the bulb. At the point that it goes to the bulb, it should drop to 0 volts and it should complete its way back to the ground, okay? There's a lot to unpack there, but for now, just loosely stay with me, and then we're gonna build on it next week and the week after, and you're gonna do experimentation on the bulbs and on the boards and build circuits and test things, okay? But if you follow me, if this bulb no worky, what I could do is check to see if it has power voltage here, check to see if it has ground, which is negative there, right? I check for positive here, I check for negative there. If I check for positive power here and it don't have it, where's my problem? Anybody think they know? It's this had power, right? So maybe first what I should do is check here. All right, I got 12.6 volts at the battery. Now that I know that, I go ahead and I check right here and it doesn't have 12.6. That means the problem's somewhere between here and here. Follow what I'm saying?
Mm-hmm.
That's the direction we're going.
Wired?
What'd you say?
A nicked wire?
A nick probably wouldn't do it. A wire that's cut, a wire that got the insulation nicked and then water got in and corroded and corroded and corroded. It's no longer a good conductor. Why is it not a good conductor?
It doesn't have a circuit.
Hard to say, yeah, but there's no clear path, right? It's an open circuit. Correct, exactly. Now, what if it went a different way? What if I checked for power? Ooh, it's so hard for me to do that. Here, and it had 12.6, but the bulb still didn't work. I'd want to check to see if it has ground right here. Now, why ground? Oh my goodness, these are not the best of terms, but I'll work with them, okay? This is what ground means. A ground means connection to the negative terminal of the battery. That's all ground means. What does that have to do with the ground I'm standing on? Not much. So why do we call it ground? I didn't do it. It's not really my deal, but the actual earth, like when you hear those grounding things, all that stuff about electricity, whatever, we actually take a grounding rod. I know because I've installed one. I think they're 6 feet, and you drive that thing like 5 feet into the ground, and you leave just a little bit sticking up. All the little terminals, you know, on your power outlets, right? Your outlets. There's like these two, right? And then there's the kind of like half circle looking weird thing. That connection literally goes to ground. So ground is like the neutral point. It's like ground is not positive, it's not negative. Like if you have an excess of negative or an excess of positive, the ground equalizes all that stuff. Makes sense? So that's what ground really is. In a car, we consider ground to be anything connected to the negative battery terminal. And the reason we do is because we take the negative battery terminal, we bring it down here, and then we bolt it to the frame or we bolt it to the body, nice clean metal, and we ground everything that's metal. So now I'm going to give you a new term, chassis ground. Remember I talked about that last week. Chassis ground is because we take the negative and we blast it onto the ground, and now everything that's metal on that vehicle is ground. So it's like negative. Kind of weird, huh? So that's why we call it ground. So with that being said, if you come over here and you check for power and it has it and it doesn't work, your next step would be check for ground and it has good ground. Let's just say it doesn't have good ground. Then you know somehow this circuit didn't make its way to the negative terminal ground. Some people have even described the negative terminal as like a virtual ground. It functions as the ground, it's the return path, but in reality, it's not connected to the earth. You see, so it is kind of weird. Make sense? Kind of feel like you got a little bit? All right? If you check it and it doesn't have ground, you got to figure out where's the open? Where's the open at? Okay, so let's say you fix that. Fix whatever, you replace the wire. In this case, by the way, the switch is on the ground side, so this switch could be defective, by the way. That could be our open circuit. But let's say you fix it. If you go to this bulb and you check and it has 12.6 volts power or voltage, and it has ground and it's good, and the bulb doesn't work, do you know what's wrong? The bulb. Okay, so you shouldn't really know this yet, but I'm warming you up, right? I'm going to explain it like this. This bulb is supposed to do work for me. What is the work it's supposed to do for me? Exactly. But the customer doesn't come in because they want you to test their electrical system for nothing, right? They came in because their taillight bulb is out, they got a ticket, they got a fix-it ticket, now they got to fix it, and then they got to get signed off, or they're going to jail, straight to jail or something. So they bring it to you, and they say, what do I need? You could jam a bulb in there. I'm cool, because they'll probably fix it. You could also pull the bulb out and look through the glass and see if the filament's blown. Those are legitimate tests, I admit. However, you can't really do that with a motor. You can't really do that with a solenoid. There's a lot of things you can't do that with. As soon as you get LED in solid state, you can't tell if an LED is good or bad looking at it. So I wouldn't rely on those tests. I wouldn't rely on the oh, it looks good to me. You know, I would rely on, test the sucker, please, do it. Okay, so then you'd say, well, let me check for the 12 volts. Oh, it's got it. Let me check for the ground. It's got it. That bulb is like a worker. That bulb is a worker. It does work, remember? If you hire an employee and you give that worker everything they need to do the job and the job doesn't get done, what do you need to do?
Nuclear.
You're fired. Get a new one in there, right? Now, let me back it up though. What if you tell that employee, hey, your job is to sweep this classroom and you don't give the employee a broom? What's the problem?
The instructor.
Employee don't give them a broom, you gotta have a broom, right? So we need to give this bulb everything it needs. If you go in there and you're like, hey, this bulb doesn't work, let me yank it out, fire it, jam a new bulb in there, and that bulb still doesn't work, how many times are you gonna do that? Before you realize the employee never had the broom. The employee don't have the broom, the floor is not gonna get cleaned, right? So our job is to make sure, hi, how you doing today? What do you need to do your job? Oh, I already know, because I'm looking at the diagram. You need 12 volts right here, you need a good connection to ground right here. We check those two things, that's it. That's how easy the diagnosis is. It's so easy to me. But you gotta have the tools, you gotta have a little bit of knowledge, and you gotta actually take the bulb out and touch the right terminal and then touch the other terminal, and then you'll be like, then you pretty much got a full diagnosis. That'll hold up in court. That'll actually help you be able to diagnose other electrical components. A heated O2 sensor, for example, with the heater circuit not working, right? When that computer tries to run that heater circuit, it needs 12 volts on the positive and it needs ground on the negative. If you verify it's got 12 volts in ground, the sensor's no good. However, if you find it doesn't have the 12 volts, then you have to backtrack to where is it losing the 12 volts? And the ECM provides the 12 volts on that sensor. So if right at the ECM it's not giving 12 volts, it's because the circuit's damaged inside of the computer. Again, you can't see that. You have to test that. So that's kind of the direction we're going right there, okay? Now the effects, we talked about it. If it's got current flow, we can make a light. We can turn the starter motor. For example, you guys have maybe had to use that the last couple days. You turn that rear defogger or defroster on. We actually have positive here, negative here, and this is a long stretched out resistor. And when the electrons go through that long resistor, they make a little heat. Not a lot of heat, but a little heat. And that's what cleans the glass, or it defrosts. It'll melt the frost on there. And then what's interesting is a battery's kind of funny. How does the battery store this energy? Like, remember the bowling ball? It has no potential down here, but if you roll it up to the top of the hill, that thing is like locked and loaded. Make sense? How do we bring a battery from no potential to 12.6 volts worth of potential at a certain number of cranking amps? Yeah, but originally, like if I got this battery brand new, this battery, without going crazy in the battery, has got plates and stuff in it, and it's got acid and stuff in there. If this battery is discharged, to bring it up to its full potential, I'd have to charge it, right? But it's sort of like where is the energy going? It's actually chemical energy. We're changing this from more of like a water based, and we're actually charging it to an acid, and that's really how we hold the electrons. That's how we build up the potential. The battery is really interesting. It's actually chemical. It's a chemical storage device for electrical energy. Kind of crazy, huh?
That's why you don't get battery acid on you.
I had a brand new jacket, brand new, and it was right around now, slightly after Christmas, and we were doing battery work in my first ever high school class, and I remember I did get a little battery acid on it, and the next day it had a big hole in it.
I think it's a new jacket.
Brand new Carhartt jacket. It was like the first day I wore it back to school. Okay, and so battery acid's nasty, that's true, so just keep that in mind. And then electrical resistance, as you guys know, we're talking about that, how it kind of holds back the electrons. That controls the amount of current. Okay, so this is probably a good spot where we'll kind of pause for a bit and let you digest some of this. More resistance means we're backing these electrons up, and look, only a couple are making it through. Can you see that? So what did the higher resistance do to our current flow?
It stopped the current.
Did it totally stop it?
It regulated?
It right, exactly. It can control it, right? So if you have a lot of resistance, you have less current flow. What if you have little resistance? A lot of current flow, right? So it's this interesting relationship. So a lot of times we focus on resistance, and the reason why is because resistance can change in automotive, like corrosion is resistance, temperature could be resistance. But technically, when we look at current flow, voltage can also change resistance. Voltage can also change current flow. So higher voltage would cause more current flow, lower voltage would cause less. That's true. But generally, we have a fixed voltage in the vehicle, right? This is the 12-volt system. So we're not super concerned about the voltage, but I feel like it's important for you to know, because when we get into Ohm's law, you're going to do calculations, and some of it's going to be higher voltage, lower voltage, how it affects the amperage, and that's true. But in practical application, most of the time when we have a problem with amps, we're probably looking at excessive resistance, because that comes from these natural things like corrosion, a cut wire, contactors that get burned and they have kind of like a film on them, these types of things. Cool, so the resistance is going to have the effect on the current flow. Again, all of them have some amount of resistance. How we measure it is ohms, which looks like this. Remember, I was not going to draw that. The omega symbol. Cool? A good conductor will have very low resistance. An insulator will have very high resistance. And then a semiconductors, those are the things we're talking about. That can be a good conductor or a bad conductor.
So when you
Influence.
solder, that's the iron wire is the conductor, so it can flow.
Solder is a good conductor, correct. So if you had a wire that was broken and you brought them together, you could, if you were janky style, you could twist them together, and that would kind of make a decent connection because the coppers touch each other. But over time, don't you see how that could cause an issue? And now you have excessive resistance, and you have the taillight that's out, or taillight that's dim.
Or
Makes sense?
door lock.
You could put a wire nut on there. That's janky stuff. That's not how we fix. Now in a house, sure. A house is different. A house isn't moving down the road and flexing, but a house is also 120 volts to 240 volts. You get away with a little bit of resistance, remember? But on a car, you only got 12 something to work with. It needs to be like a really clean connection. So when we got a whole day on wire repairs and soldering.
Yeah.
When we do that, it's got to have low resistance. Soldering it is good. There's one negative of soldering, two negatives. One is you're working basically with a hot object inside a customer's car, and you can catch stuff on fire. Two is solder's amazing, but it's not flexible. So in the correct point, solder's perfect. But if it's like a wheel speed sensor wire that has to flex, the solder's not really going to hold up right there. It's just going to end up, it's brittle. It's going to break.
Also, if you don't do the solder right, you can
True.
lose. You can, because that's what happened in the Camaro, right? Is it Camaro?
Oh, yeah, where you guys had to fix the wire.
Yeah.
Yeah, that was
Like
exactly.
the soldering, there's like a gap and it's not catching.
Correct.
anything.
So when we do our wire repairs, it's important that we're considering the resistance of the circuit. We don't want to add resistance. If we do, you know, you might have, the wire might look like it's together, but it might not function, type of thing. So we also have butt connectors where we can crimp them. Then we got to worry about water, so we really need to seal them up. Electrical tape is okay, but heat shrink is better, you know. So when we cover that, it all ties back to this type of thing. Okay, so I think right now, go ahead and give me a pause. All right, so right where we left off, talking about resistance, let's get some practical application of resistance. So if you're gonna have a longer cable, more resistance, a shorter cable, less resistance. If you're gonna have a smaller cable, more resistance, wider, like a bigger gauge, sometimes we'll call that gauge, that's gonna be less resistance. So when we start looking at wire sizes, there's something you have to understand right here. If you have a system that's gonna require more amps, so let's just say, I heard some thumpy boom boom music out there. Let's say you want some subwoofer that's gonna be boom 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 boom. The subwoofer is actually a magnet, for the record, and depending on the signal it gets from the amp, which depends on the signal it gets from the head unit or radio or whatever, it's gonna actually move that magnetic field, and that's gonna pulse that cone. You ever notice the subwoofer is kind of like a dish or a cone? And that's gonna move air, and then that air is going to move air against your eardrum, and that's how you're going to go deaf with your boom boom and your you know, or whatever. But somehow it's better when it hurts a little bit more. Apparently, based on what I listened to out there,
Makes the voices go away.
yes, it does make the voices go away. There's probably some medication for that potentially, but we'll stick with the subwoofer. Now, that big old subwoofer, to really make you go deaf, you're going to need a lot more electrical current, right? So if you want a big amp and you want this big sound, then let's say you're trying to set up a system that's going to pull 100 amps. You need a cable that's going to take 100 amps. That's going to be all determined by the diameter, so the gauge, exactly. And it also has to do with the length. The reason they don't talk much about length is because cars and trucks are about the same. You might have a 15-foot long car, a 24-foot long Yukon XL or a big Suburban or something, but that's not a big difference. If you were trying to run that system in a house and you were going to run that wire 400 feet, now we'd be very concerned about the length. But because cars are kind of similar, we mostly just talk about the width, which is the gauge. So you got your 4-gauge wire, that's like battery cable size. You got like a 2-gauge, a 1-gauge, a 0. Then you get into the 00, or sometimes we'll call it like 0-aught, 1-aught, 2-aught, like that. Those are really big wires. That's all going to have less resistance. And then when you get into temperature, remember, the hotter it is, the more resistance. So now I want to apply that a little bit more to the boom boom. Right? We can use the boom boom sound system.
Yeah, that's what I'm trying to do right now.
It is, huh?
I'm trying to get them. Put that in my car right now.
Okay.
I'm rebuilding my car.
I'll establish a couple things just from the scientific aspect. So when you're pulling a lot of amps, that means a lot of electrons, right? Not just a single file. There's going to be like bunches of electrons moving through there. That's going to make more heat. And if your wire is too small,
It's gonna melt.
Don't burn them out.
exactly. And so that's why running too small of a gauge wire would actually potentially cause a fire. So when you use the bigger wire, it can handle more amps, it stays cooler. What's interesting about the wire though, copper doesn't really burn, at least in that
It's insulation.
heat level, it's the insulation.
Yeah.
So if you get the copper so hot due to way too many amps and a too small of a cable,
Yeah.
the insulation will catch on fire, it'll catch the carpet on fire, and then the car will be up in smoke. So one of the next things we talk about
It's the
is
fuses.
exactly.
Shut
Now,
off.
if you need 100 amps, I would use a 100 amp fuse, but then you have to have a wire that can take the 100 amps. So when we talk about this, and you're looking at the size of the wire and stuff, this can handle a certain amount of amps. But if you don't have a fuse on there, that's pretty unsafe because this can handle a lot of amps, but let's just say this wire gets pinched and next thing you know it's like shorted to ground. Even the biggest of wires have a limit on how many amps they can take. So that's why we start to fuse stuff. The reason I bring up fuse now, even though we haven't covered the components, is because the fuse is always going to be matched to the wire size. it's like if you had that 100 amp system and you put a 100 amp fuse in and you really got it rock'em, sock'em, boom, boxing, whatever, and it blew the fuse, you can't just put a bigger fuse in unless the wire can handle that fuse size. So if this wire is good to 100 amps is the fuse size, that's it. You don't put a 125 in because then the fuse will no longer sacrifice itself to save the wire's insulation from burning. Make sense? So when we get into the wire size, it's all about how much work does it need to do, and that's why we use that size wire. So let's say that you were just going to run some LED lights. They probably don't pull a lot of amps, so you don't need this big, huge wire. Could you use this big, huge wire? Yeah, if you want to waste money. Sure, go for it. There's nothing wrong with using too big of a wire, but generally we don't want to waste money when they're engineering the cars from the factory, right? So when they engineer it from the factory, they put the wire size that circuit needs. They don't upsize it. They don't like put it bigger just in case somebody wants to add more lights and add more amps and add more subwoofers and all that. They use the correct size wire. So
And
when
the
we
alternator matters though, right?
True. So I'll come back to that one. It says overall, but when we're purely talking about wire size, the wire is sized by the engineers for the work that circuit's going to do. Make sense? So, like, to apply that, let's say we had a problem with this wire and we had to cut a piece out and put a new piece in. What size wire should you put in?
Same size, right?
Same. If you had to, you could put bigger. You cannot put smaller. You understand? Because the smaller wire has more resistance, which will make it hotter. And this little section of small wire could be the section that starts on fire because it's undersized. This wire right here might only be able to handle 80 amps. And you have a 100 amp fuse. So once this thing's running 100 amps, the fuse, if it's 98 amps, the fuse won't blow, but this wire will be overheated and it could cause a fire. Make sense? So we're linking the wire size to the fuse size and to what the whole circuit is designed with by the engineer. Now, if you're going to add stuff, you're going to do the winch, you're going to do all this type of things, probably the accessories you buy are going to come with either the wires or they're going to say what size wire. But if you want to get really technical, you could actually calculate it. Did you know that? So we'll introduce you just a tiny bit to the Ohm's law where you can do your own calculations as kind of like an electrical engineer. It's like the very basic task of an electrical engineer would be to calculate how many amps the system's going to have. And then you can determine what the wire size needs to be, right? It always needs to be a little bit more. If it's gonna do 9 amps, you could probably do a 10 amp circuit with a 10 amp fuse. If it's gonna do 11 amps, they don't make an 11 amp fuse. You're gonna have to bump it up to 15, right? These types of things. So just visualizing that should make sense. Now, looking at the conditions of the wires. You see this wire right here, it's like basically an open, but there's a couple strands maybe still there.
Not a good connection.
Not a good connection. More resistance. That's going to have like a lot of resistance. This right here is actually going to get hot, and also your amperage is going to be very low. So your bulb is going to be very dim. Your subwoofer is probably going to, it wouldn't be the sub really, it'd probably be the amp. Your amp is probably not going to have enough power to keep the correct sound. It's going to start to sound bad. If not, probably shut off for protection. Additionally, so like you got broken with the strands, you got nicked. Additionally, a big one right here is that corrosion or a loose connection. So if you have, we talked just a tiny bit about terminals, right? There's the male terminal and the female terminal, and they should have like a good fit, so that way they have a good surface area and contact. If you had corrosion there, you've added resistance. If you had the female terminal, let's say, was affected by a two-legged varmint. You ever heard of those, two-legged varmints? Who knows what a two-legged varmint is?
People.
Yeah, people. Let's say you had Mo, the mechanic, in there. And mechanic. There Mo was. My friend mechanic was in there. He took the probe and he's like, oh, let me test for power. And he shoves that terminal in there. And now that female terminal is like this. And the male terminal is like this. That's excessive resistance. In fact, that could be a full-on open circuit, right? So it's really critical that where we make our connections, you can't be having corrosion, You can't have like
Play.
a damaged terminal. Same, like sometimes the male terminal can be bent and then that'll damage both, right? And so we could make this less a health class and just say if the male terminal's damaged, the female terminal ends up damaged. If the female terminal, so like you might look at a connector and not just, you might visually look at it and say like, oh, that's messed up. Well, the correlating terminal's probably messed up. You might need to replace both. You can measure that for the record. If you were to go up to a connection like this, you can see that that's messed up, right? Anybody who's worked on stuff, they tend to say like, oh, look for corrosion, look for green or like powdery oxidation and rust, and all that's really good, but I don't want to have you come up short. You can measure this. So if you thought a connection was no good, my recommendation is measure it. It's good to use your eyes, and by all means, if you see something that's messed up, for sure, fix it, but I don't want you to stop there because there's hundreds of thousands of mechanics and DIY people and YouTube certified individuals and whatnot that will say like, oh, check all the connections. Then they'll check all the connections, everything will look good, and then they're out. They're tapped out. They're like, I don't know, I can't fix this. I'm not really sure, right? So by all means, use your senses, but I want you to get in more of a habit of measuring, because sometimes you're not going to see it, but you'll be able to measure it. So if I were to go over here and I were to put my lead on this ground and on this terminal, I could tell how much resistance is there, and I could tell if it's excessive. Even more practically, I could measure the voltage drop right there, and I could really tell if that connection is good or bad, right? Then I could clean it, make it look pretty, maybe even dielectric grease, maybe hook it up nice. Then I could measure it again and verify that it's actually fixed. Could you see how that would lead to less misdiagnosis, less comebacks? Remember the thing I was saying in strategy-based diagnosis, it's all about fix it right the first time? Me measuring it, repairing it, and then remeasuring it and verifying I fixed it that's the direction we're trying to go to really make sure that we're nailing these down. So the corrosion's gonna be a big thing. Loose connection, that could be like this bolt's loose, but remember that could also be the male-female terminal type of fitment issues. I've actually seen several cars that were lemon logged for that. Can you imagine, you got this beautiful car, $30, $40, $50, $80,000 car maybe, and it's in the shop several times and it gets lemon law bought back because there was a pin fitment issue, meaning the female and the male terminal didn't have the right amount of tension. It's happened, I've seen it. So what I want you to get really good at is that type of diagnosis, because the manufacturers and the shops, that's really who they need. Especially the manufacturers are like, if you can fix that car and not have it lemon lawed, you're worth a lot of money. Make sense? So kind of building off of that, there's the normal resistance as we've talked about. So this is the same circuit we've viewed, but we've added in the fuse. So remember, the fuse is to protect the wire, really, that's what it's to protect. The fuse isn't really there to protect the load typically. On some motors, sometimes they'll do some stuff like that, but like if this bulb gets too much current flow, the bulb filament will just poof and it's gone, and it doesn't make fire because it's inside the glass. We're not worried about the bulb. We are worried about this wire getting too hot and the insulation catching fire and having what we like to call the thermal event. Make sense? We can't be having the cars catch on fire. So we fuse it, right? Mainly to the wire size. Cool? So like if we were to rewind, you'd say this bulb is this amount of ohms, and so it's going to have this amount of amps. So if it's going to have 8 amps, we'll run a wire that's good for 10, and we'll put a fuse that's good for 10. Cool? And it should never hit 10, and if it does, the fuse blows, but the wire is saved. Cool? Boom. Then I want to talk about the resistance. The resistance in this bulb is 10 ohms. It's 10 ohms because they made it 10 ohms. It's designed to be 10 ohms. 10 ohms of resistance is going to give us the correct amount of light and the correct color of light, all that type of stuff. Cool? So if this is 10 ohms, the total circuit resistance should be about 10 ohms. We don't want added resistance down here. Okay? If this, you see right here, we haven't covered symbols yet, but this is a switch. You know what a switch does? Yeah, it makes contact or it doesn't, which means it makes a path or it doesn't make a path. Reworded, it makes continuity or takes away continuity. Reworded, it gives open resistance or no resistance, right? That's what it does. What if we were to have a bunch of corrosion internally on that terminal right there? 10 ohms worth. What's the total resistance now with 10 ohms added on the switch?
20.
Exactly. Now, mathematically, that would make your amperage half. And I'm going to prove it to you a little bit. And then a little later, you're going to do more and more calculations. But if you're following what I'm saying, we were supposed to have about 10 ohms, maybe even 10.1, because the switch and the wires have a little tiny bit. But instead, this switch is messed up. Now it has 20 ohms. That's going to make, you can picture the electrical flow trying to go through here, and it's like, yeah, I'll push my way through there. But it's like, but now I also have to push my way through here. That's going to drop the flow. That's like two kinks in the hose. The firefighter goes to save those cats and they got two kinks in the hose, just give it up. Not happening. Make sense? It's supposed to have one kink, and if you wanted to think of the firefighter fighting the fire, the actual only kink in the hose should be that nozzle, and they control the resistance on that nozzle, right? They want some resistance so it gets a good stream. So that would, in a sense, be the nozzle. This down here would be the kink that they didn't know about. It's not, the water's not going to spray right. You're going to have reduced electrical current. What's this bulb going to look like to your eyes?
It's gonna be brighter.
It won't be brighter. It's got less current.
So it'll be less.
Yeah, what's less?
It'll be dim.
Dim, exactly. Dim's what we call it. Yeah. So when you look at a let's say a headlight and it kind of looks like you got punched in the eye because one's dim and one's bright, there's probably excessive resistance in the circuit for the dim one. What could the resistance be? Well, we talked about it, right? It could be this last page. It could be all this stuff. Maybe somebody put the wrong wire in, probably not really likely. Maybe somebody ran a ton of wire and looped it around and threw it under the hood, and then probably not likely. What is likely though? Yes, yes, yes. These right here are the things that we see on a daily basis. These over here, and it's a little bit more engineering style, it's something you need to know, because look, I know what you're gonna do. You're gonna customize some stuff, you're gonna add some things, you're gonna wire some things, I know that. So you do need to understand the sizes and the temperatures and stuff, but the reason the cars end up broken in the shop is this right here. All the time. Okay, I told you about the two-legged varmint who stabbed the terminal and now the terminal's all blown out, right? What do you think about the little, what other type of creatures you think might cause some wiring issues? Yeah, rats, mice, I've seen squirrels, right? Mm-hmm. So if a mouse gets in there and is chewing on the wires, let's say if they're really ambitious, they'll chew the wire right in half, and your headlight will be out. It'll be inoperative, period. You'll put a bulb in, it won't fix it. You'll measure it, and you'll be like, oh, there's no voltage power to the bulb. Then you'll go back, and you might find the rodent damage. We call it, like if you write it up on a repair order, we call it rodent damage. Because you don't really know, is it a rat, is it a mouse, is it a field mouse, we don't know. You don't know. Is it the protected endangered species, the infamous kangaroo rat? I don't know. But it's a rodent, we can tell.
What about a New York subway cat?
Oh, if you're there, not my problem. I left. Don't deal with that anymore. Okay, but however, whatever damages this stuff could be due to that. Let's say that mouse was maybe a little lazy that day. They may chew the wire, but not all the way through. So it might cause some intermittent issues. It might touch, not touch. Either way, they broke the insulation, so corrosion is going to occur because water is now getting on the copper, and the copper is going to start to oxidize and kind of like rust in a way, right? So they cause all these types of problems. Those problems cause less amps to be able to flow because the increase in resistance, remember? You increase the resistance, that lowers the amperage, the light is dim now. Make sense? Because the total resistance has gone up. Now you got resistance in two spots. Cool? But the good news is, look what it says right here. The fuse plus the switch plus the wiring should be about or less than 0.1 ohms. How could you test if those items are good? Follow what I'm saying. Here's the spec. How could you do Come on, talk with me. You don't have to know exactly how, but give me an idea. Exactly. That's why I like this. Like, it's not yeah, use your meter. Use your meter. And that's some of the things that we're getting into in the next couple weeks is like, hey, if you kind of understand this and the car came in and it's got a dim bulb and you think it's excessive resistance, cool. Put your theory to the test. Remember strategy-based diagnosis. Measure it. Right here, I can measure that switch. I can measure this wire. I can measure all these things and I can prove it out. I can prove it is or isn't the switch, right? So Sloppy Mo, the mechanic, is like, well, in my opinion, I think you need a new switch. And then the customer's like, okay, cool. Is that going to fix it? Well, I don't know, but you should put it in there. That's not the direction we're trying to go. By the time you make a recommendation, at least in a perfect world, you should have been able to prove it, measured it. Hey, I measured your switch. You're supposed to have 0.1 ohms. You have 10 ohms. That's too much. So then when you put the switch in, you're very confident. Now that doesn't always mean that there's never another issue. Sometimes you have two problems. I get that. Other times you have intermittent problems where it's like you measure the switch and the switch tests good right now, but under some conditions, maybe when it's a little hotter outside, it's bad, or sometimes intermittents can kick our butt. But you should be trying to prove your diagnosis, not just guess.
Logical reasoning.
And you know what opinions are like? Butts. Everybody's got one and they stink. I don't want your opinion. Okay, now, Ohm's law. Just a little bit, okay? We're going to do a lot more Ohm's law later, but I want you to overall understand how Ohm's law applies. You don't do that much math today, but you're going to pretty soon. Okay, in Ohm's law, if the circuit had 1 ohm of resistance and 1 volt power, remember that's like the electromotive force, that's a voltage, it would have 1 amp of current flow. That is so proportional, isn't it? It's interesting how that works. 1 ohm with 1 volt, you get yourself 1 amp. However, if the resistance doesn't change, a higher voltage would produce more current. A lower voltage would produce less current. Does that make sense? More pressure is going to make more flow. Less pressure is going to make less flow. Yeah, exactly.
So let's look at it, what are they called? The slides, the water slides.
Sure.
So if it's pushing me
Bigger
with
slide.
water, no, if it's pushing water to get me,
Sure.
that means it's more current.
It's flow.
Yeah.
Yeah.
More pressure, more flow. I'll tell you what, I'll word it in this way. This is a coined term. I'm going to call it Hind's law. Okay, this is Ohm's law. I present to you Ohm's law. Now I present to you Hind's law. Okay, this won't be the first time I'm going to say this. Hind's law is the ketchup bottle. Now, I'm looking at some of you and you're probably laughing, but the most spicy type of salsa I can have is pretty much ketchup. Okay, but let's just say it's ketchup. Whatever it is, I'm putting ketchup on. If I get the ketchup bottle, okay, and I want to squeeze a certain amount of ketchup out, how would I make more ketchup come out?
Squeeze it up.
More pressure, huh? More pressure. Squeeze it harder. That's right. Okay.
So that's like okay.
Yeah, higher voltage, higher pressure, higher squeeze, more ketchup flow, more current flow. Boom. Okay, but let's think about it the other way. Less squeeze, less pressure, less ketchup flow. Cool? That's how you understand voltage effect on amperage. But the reason I like the Hind's law, it's a coined term by the way, it's my term, is the resistance factor. Let's say there you go ahead and you're about to use that ketchup right there, and that ketchup right at the bottom's kind of crusty and it's got like some added resistance, if you will. And you squeeze it the same as you squeezed it before, how much ketchup's gonna come out?
Not a lot.
Less, right? Because it has too much resistance. The resistance is the crusty, nasty, old ketchup because you haven't used it in a while and whatnot, okay? So how would you get more ketchup to flow?
More pressure.
You could apply more pressure, that's true, but if we're talking about just changing the resistance, I like clean it out. You can eliminate the resistance. If you eliminate the resistance, you're lowering the resistance, that'll restore more amperage. Make sense? Hind's law, coined term.
I don't like ketchup.
Would it have been better as mustard?
No.
I had somebody explain it to me as mustard. He was really good, but then I made it ketchup because I made it Heinz. I wanted to be, okay, you got it. Man, just for you. So now let's just say here we've got a circuit that's 12 volts. If it has 1 ohm of resistance, it will have 12 amps, okay? don't struggle too much with the math. I made a point to you. Before we had 1 ohm of resistance, right? But we only had 1 volt, so we only got 1 amp. If I keep the 1 ohm, but I make it 12 volts, it will increase it to 12 amps. And it's always proportionate. There's a whole mathematical formula, which we're gonna get a lot of practice on. And you're gonna like it. And then somebody's gonna make the argument, I've been working on cars for 40 years and I've never had to do Ohm's law. And you know, that's probably true. So don't think this class is all about how to do Ohm's law, but I want you to really understand the relationship and understand that there's an actual formula and it's proportional and it works every time and it's like actual science, you know, like the scientific method where you can observe it and study it and predict it over and over and over, and it's like, that's Ohm's law. Every time, Ohm's law works every time, all the time. If it doesn't work, there's something wrong with the experiment. Okay, so if you were to do lower voltage, right, like let's say I were to do a 1/2 volt, how many amps do you think I'd have?
Half.
Half of that.
Exactly. See, so you're understanding. You don't have to know the math, but you're understanding the concept. Increasing the voltage increases the amps. Decreasing the voltage decreases the amps. Increasing the resistance decreases the amps. Remember the Heinz law, it's crusty. No ketchup. Decreasing the resistance, that ketchup. You want to decrease the resistance the most on that Heinz law ketchup bottle? Take the cap right off and see what happens. Blah, blah, all on the ground, right? Too little resistance will cause a lot of amps. That's almost like a short circuit, actually.
I like that movie.
Yeah, okay, don't even know what you're talking about, but I'll go with it. So here's the teeter-totter. When resistance goes down, current flow goes up. When resistance goes, I said that all backwards. Let me back up. When resistance goes up, current flow goes down. See, the resistance is up, current flows down. It's opposite. When the resistance goes down, the current flow goes up, right? This right here, this is your crusty Heinz law ketchup. It's got some yucky stuff, not a lot of flow. Clean it all out, less resistance, more ketchup flow. Being electrons, of course. Cool. And then, just to introduce you, here's how you actually do Ohm's law. E is electromotive force. We measure that in volts. So if you want, you could always make EV, okay? E could become V, volts. And then I is the current flow, which we measure in amps or amperes. Amperage, if you will, is I. R is resistance, which you measure in ohms. So you could even redraw this as V, A, and the ohm symbol, whatever, it's all good. If you wanted to figure out Ohm's law, which we're going to practice, but not right now, you could actually just use this circle. You could memorize this circle. What are you trying to figure out? You'd cover it up. So let's say that you're trying to determine the resistance. Put your thumb over the R, and what do you have? E and I, right? It's E over I. You know when you have a fraction and it's E over I? It's E divided by I. You literally just takes the volts divided by the amps will be the resistance. Or let's say that you want to know the voltage. You cover the voltage. It's I times R. It's amps times resistance will give you the voltage. Or let's say that you want to know the amps. It's cover the amps, E over R. Voltage divided by resistance. So it's a very interesting law. This individual scientist way back in the day figured out there's this very direct proportional relationship, volts, amps, and ohms. If you know two, you can determine the third. There's a type of math this is. Anybody know what type of math this is?
Algebra?
Exactly. Algebra can be useful. If you know two, you can figure out the third. This is the formula. There's technically three formulas, but this circle can give you all three of the formulas if you just have access to the circle, right? So if you can know two and know the formula, you can get the third, and it's always consistent, all the time. That's real science right there. Okie-dokie. Now, this is my favorite picture, right here. You could Google this if you would like, and if anyone wants to get it tattooed, you can have extra credit. One point of extra credit. You gonna do it? You gonna do it?
Why not?
If it's the lower back, 10 points.
Does
10
it have,
points in Gryffindor.
does it have to be, with ohms? I'll get the little guys.
No, it's gotta look just like this, and this guy's gotta have a hat.
I got somebody with tattoos.
The hat stays on.
The hat stays on.
Okay, so here you go. Who's trying? The amps, remember, are kind of like the electrons, really. Who's pushing? Volts are pushing, trying to push the electrons through, right? If volts were to push harder, don't you think amp would go through?
No.
Yeah, if you increase the volts, you could increase the amps. Make sense? But that would be assuming ohms stayed the same. Now, what if volts push the same, but ohms like kind of let up a little bit?
It will go faster?
Exactly. So this literally, you might not want to get it on the lower back, because if you ever had to look at it, you might want to be able to see it. So now I think about it,
Okay, I already got these.
when you go to take your ASE, you could be like, by then you should memorize this. You should understand this. You don't need to get this as a tattoo.
You'd have to get a mirror and put reverse on it.
Yeah, you'd be like, I don't know this question. Let me do a quick selfie. They don't let you bring your phone in the test center, though.
No, it's a three-person tattoo. One has to be volt, one has to be ohm, and one has to be amps.
You need 3 people to get this? You need them all together? Okay, now let's just say, okay, let's give it some variables. Let's see if you're picking up on what I'm saying. What if ohms were to pull tighter? What would happen to amps? Yeah, ohms pulling tighter is adding resistance to the flow, right? So it's going to be less and less flow going through. Now you can kind of visualize it. So depending on what we do with the ohms, with the resistance, if we lower the resistance, more amps will flow. If we increase the resistance, less amps will flow. Cool?
So it could be like the dashboard light. The little switch, right? Because you dim it, so you dim
Okay.
Yeah, right.
That one is called typically that's going to be like a rheostat. That varies the resistance. So if it's a dimmer and you put the dimmer to the most dim setting, you've actually added resistance. That's going to pull this tighter. There's going to be very few amps. It's going to be dim. Exactly. Then when you put it to the brightest, right, you roll it up, that actually decreases the resistance, which means more amps flow through and your lights glow dimmer. That's exactly right. So in here, we're trying to show that the ohms could be variable. Now, in a typical lighting circuit in a car, like a headlight, we don't have a dimmer though. So really, it should just be on or off. It shouldn't be like, bring them up, have brighter lights or dimmer lights. I mean, yeah, you might have high beams, but high beam's a totally different bulb in a typical system, right? It's the high beam bulb has less resistance. The low beam bulb has more resistance. It's going to be less current flow on the low beams, more current flow on the high beams. It's just how it is. Okay, but now you guys can see if you want to increase amps, you can go ahead and increase the voltage. Or if you want to decrease amps, you can decrease the voltage. In a car, we don't generally change the voltage though. So mainly we're focused on this fella here with the hat.
There's so much hate in his eyes.
Can you see him? They're like black beady eyes. He looks like he's enjoying this too much. There's really something wrong with him. All right, so like what the book shows is another pretty good one. If you were to look at this fire tank, the height of the fire tank, because of gravity, is actually going to have a varied potential, right? At the top of the hill, that bowling ball had more potential. That's like more voltage. So you're going to have more pressure. Right here, they call this head pressure. But for our purpose, because we're doing electricity, let's call it voltage. You have a certain amount of voltage. This is going to be electrical pressure. Now, right now, the hose is kinked, so that's going to be increased resistance, and you're going to just get, this is them trying to put the fires out. I know I'm sorry, but like, that's a perfect example right there. Now, why? Actually, in their case, to be honest with you, it wasn't really an issue of added resistance. It was an issue of they didn't have the pressure. So reduced pressure, even though your hose is clean and clear, you're going to be like, I'll save your house. Nothing. What are you going to do with that?
Not enough volts.
Didn't have enough volts. That's exactly what the firefighters didn't have. They did not have the pressure. They didn't have the voltage needed. It's a perfect visual. It's also fresh in your minds. Okay, so that's kind of the visual. Now, in electrical terms, the battery is the voltage, right? And then right here, we're trying to have this defroster do a certain amount of work. That's like the water spraying and helping put out the fire. But we have a resistor, we have excessive resistance in the rear window defrost switch. So if this defrost switch had an open, that's like the kinked hose. You're gonna have low amps, maybe no amps. Make sense? So this one, very visual. This one is like, today when you rolled in and we started this sucker up first thing in the morning, if I were to show you this and I were to say, you know, this switch has excessive resistance, you wouldn't really understand what the effect would be. So we're trying to build you up to that in several different ways. Everybody learns a little different. If this has excessive resistance, do you see how this is going to have less amps? It's not going to get as hot. And next thing you know, your window defroster doesn't work and your back window's all foggy or, you know, frosted over this morning. And the customer says, oh, my rear window defrost or defogger doesn't work. Well, no problem. Let's get into it. You know, we jump in here and we'd say, how many volts are available? If you only had 3 volts available, you know you got resistance back in here somewhere. You hunt it down. Be like, oh yeah, your rear window defroster switch is no good, or maybe this connection, remember the connector is no good, or maybe the wire got chewed by the rodent, or what. There's all these possibilities that cause this not to make enough heat, and you got to be able to prove it to me, really to yourself and to the customer, why that's the fault. So when you sell the customer something, it's going to fix it. You selling a wire repair, you selling a switch, you selling a defogger, by the way. It could be this. If you have 12.6 volts here and you have ground right here and it still doesn't work, this is not good, right? This employee has everything it needs to work and it's still not working. You got to fire the employee, you get a new employee. If it doesn't have what it doesn't, if the employee doesn't have what it needs, in other words, if the load isn't getting the correct supplied voltage and the correct path to ground, you got to fix those. Okay, that's the visual. Cool. And then I also want to point out, electrical energy that's lost to resistance is converted into heat. Okay, so if you have, let's say, this I've seen, if you have a headlight connector that gets connected to your bulb and the connector gets a little corrosion and stuff like that, it's resistance, right? Which makes what? Tell it back to me. Heat. And next thing you know, the plastic is melted and stuff. So if you see a headlight connector and the plastic's melted, you're like, oh, that's got excessive resistance. You have to know that. Looking at it, it's like, remember, you're going to be the doctor. So you're going to be like, oh, the plastic melted. I wonder how that happened. You got to understand this. That plastic is melted probably because the resistance was excessive. So you may look into, like, is it a wire harness? Why is the resistance excessive right there? Make sense? It does happen. And then the amount of heat generated by resistance is directly related to the amount of current that passes through it. So I'll add to this again. Yeah, current and amperage. The more amperage that's going to go through, the more heat it's going to make. So if we tie it back to those headlights, anybody ever seen the Sylvania Super, what are they called? Silver Stars? Some of those headlights that are brighter, they're brighter because they pull more amps. When they pull more amps, they can make more heat too. So we've actually seen aftermarket headlights that glow so much brighter, they make so much more heat, they can actually start to melt the headlights.
The plastic cover.
Exactly. Melt the cover, so higher amps also means higher heat. It's kind of interesting. They both can result in heat issues. Cool. And then reminding, good conductors have a low resistance, insulators should have a high resistance, and the resistance of an object is constant and does not depend on the amount of voltage or the amount of current passing through it. So the resistance should be the resistance. Makes sense? It shouldn't be like if you push more, all of a sudden it opens up. Like it's not really like the Heinz law in that way. If you wanna clean out the crusty, nasty resistance on the bottom of the ketchup bottle, you squeeze that sucker, it might blast all the chunks out. Electricity doesn't work like that, so in some ways it's good, but in other ways it's not really. The resistance is the resistance. You don't clean it out or clear it out or shock it out. You have to actually repair it. Now, speaking of resistance, just for fun, this is a resistor. I don't know that you'll ever need to really do this in practical application. However, you should know there used to be a place called Radio Shack.
There used to be one in Menifee.
Yeah. You guys have never heard of Radio Shack.
I've seen a Radio Shack.
Big
Yeah.
inside of radio.
Okay.
Why did they shut them down though?
I think they're just too expensive. Anything Radio Shack's got, you can get on Amazon tomorrow for half the price.
Just like.
But that's my guess. Plus, people aren't really fixing stuff. Yeah. Back in the day, if you had a broken radio and you could go in and you could measure the resistor was bad, you could replace the resistor. Which resistor would you get? You'd have to see the colored bands. So each one of these means something. So like the first digit, for example, let's just say it was green, that would be a 5. Let's say the second digit was, I can't quite tell. Let's say this is kind of like yellow, that'd be a 3. The third was a 3. That would be 533. And then let's just say it was 0 is the multiplier. That would be 533 ohms. And then the tolerance, let's say it was something cheap, you might get 10%. So it'd be 533 plus or minus 10%. So you're really looking at like, that's a little bit of a tough number for me to come up with. 533, 10%, that'd be 53. So you're looking at like 480 something to 580 something, whatever, something like that. Okay, and really we're not the engineers. Okay, so if you ask me a lot of this stuff, this is things that I learned when I was in your seats, and have never had to apply it since ever, because this isn't really what we do. Radio Shack, fixing electronics, that type of stuff was cool. It's not something that's really done in cars. It's not done at all. We don't ever go in there and solder in new resistors. The most common place you'll find a resistor is your blower motor, and it's like a whole pack of resistors, and you disconnect it, and you connect a new one. You don't really, you don't like go in and do any repairs. We don't really do repairs like this. However, if you got into something where you were to have to do this, let's say you're gonna build a spaceship, you build spaceships and stuff. You're gonna go work with Elon, do the SpaceX thing. First off, if you need a resistor that's a 533, remember green, yellow, you're probably needing that tolerance to be pretty tight, right? That spaceship's gotta be like pretty exact. You probably don't need the 10% or the you're probably gonna need like a 1% tolerance or maybe even less. Make sense? So the tolerance is showing you how far out of spec it can be, like normally. And then the colored bands are going to tell you how much resistance it is. If I was really worried about it, to be honest with you, I'd probably never actually try to figure this out based on colored bands, to be honest. I'd probably get my meter out, I put it on ohms, and I measure it, and then I would know exactly what the resistance is, right? So this is a little more electrical engineering type of stuff, but still interesting, and it's still good that you understand when the electrical engineers build the electronic and electrical components, this is the type of stuff that they're using and doing. It's just out of my area of expertise, quite honestly. Okay, kind of fun? Don't make me go get the resistors and pass them out and have you sort them out and tell me the value of each one of them, because I've seen that trick done many times. Okay, like if I come unprepared and I don't know what to do, I'll just like say, hey, I need you to organize all these resistors and lay them all out, and then be like over here picking my nose or something, and you'll be like working really hard, and then at the end of class, you know what I do? Throw them all back in the same bag. I've known some people that would do that, some instructors who do that. Mostly high school level. I'll keep you busy. Same with bolts. Throw the bolts all over, have them organize the bolt and write what size they are, and spend all class doing it, and then when you're done, put them all back in the same bucket. So just busy work. Some of you military people, you may understand sometimes some of that, huh?
Yep, mopping in the rain.
Dig a hole, mopping in the rain. Dig this hole, have the next people come in, fill that hole, then dig it again, fill it again. Right? So not trying to give you super busy work, but just trying to get you to understand these concepts. Cool? Okay, and this is kind of showing you all those effects, right? If a current flow through resistance increases, the voltage used by that resistance will increase. Okay, that's kind of weird. So when we start to talk about the load, you got to understand something. The load is going to use up that voltage. So let's say it's the bulb. If the bulb has a full 12 volts available to it, the bulb will use the full 12 volts. It will glow nice and bright. But when we start to have multiple resistances, the resistances will start to basically take their cut. So the visual representation for that is, who's got siblings? Let's just say we'll make up an imaginary family right now. You got your parents, and your parents have $12 of allowance money. That's the 12 volts. The parents are like, all right, kids, we're going to hand down your $12 of allowance. Let's say there's one child, only child. How much does the only child get? $12. That's the perfect scenario. If we have one bulb, like if I were back up on that image, if we have just one bulb, this bulb is going to get all the voltage for itself. Cool? All $12. Don't spend it all in one place. Allowance. However, let's just say that this becomes another load, right? It's not supposed to be. It's just a switch. It should have like 0.1 ohms. But let's just say, for an example, this switch got 1 ohm. Now it's like having twins, and they're of equal size and strength. Who's getting how much? 6 and 6. Exactly. Now you have a bulb that's only getting 6 volts, and this switch is sucking up 6 volts. So if we were to do diagnosis on this, you'd actually measure, okay, we have 12 volts coming in, we have 6 volts going out. Why 6 volts going out? Because the first brother, we'll say, took the cut of $6 and then handed the $6 down, because they're of equal size and strength, right? So if they try to take all 12, the other brothers would be like, hey, I'm just as big and strong as you. I'm taking the 6. Make sense? They're equally matched. So if it was 1 ohm and 1 ohm, this one's going to take 6, the amperage is going to be crappy, and this thing's going to be dim. And then 6 volts is going to be consumed right here. But you're not going to see it. It's not like it's going to glow or anything. It's just going to be like, why do I have a loss of voltage? Where's my voltage drop? Okay, that's what that electrical concept is saying. When you add resistance, the resistance is going to consume a proportional amount of voltage. So you never want to add resistance where there's not supposed to be resistance, because it'll consume voltage. Kind of make sense? Now, what if we were to have, technically there's 2 brothers right here. What if this one was 1 ohm and this one is only 0.1 ohm? How much is this one going to take and how much is this one going to take? It's actually a formula. You'd have to put it into proportions. This one's probably going to take like 11.9, and this one's probably take like about 0.1. Makes sense, because it's an ohm and this one's only 0.1. Actually, if this one's 0.1 ohm, it's going to be a tenth, so it might even take a full volt. This one might take 11 volts and this one might take 1. Make sense? 0.1 ohms would actually be a little high. Cool, so it's always proportional. Now, if you really wanted to get super technical, I'll tell you why knowing that's important. When we start to get into sensors and things, we'll use 2 resistors, and we'll have the resistors different like one resistor will be a variable, so an engine coolant temperature sensor. That's a resistance that can be maybe like 100 ohms or 1,000 ohms. But then what we'll do is we'll put another resistor in the computer that's 100 ohms, and basically we'll send the voltage through that first one at, let's say we use the 5 volt reference. If you have 2.5 volts at the end of that first resistor, that means this resistance is the same as this resistance. And that let's say 100 ohms worth of resistance on a sensor can tell you what temperature something is. So it's like way down the road, but that's one way that we can apply these concepts to actually know what your coolant temperature sensor is. We'll use what's called a thermistor. The thermistor changes resistance with temperature, and we'll put it in line with another resistor, and the computer will be able to calculate what the temperature is based on how much voltage the first resistor consumes. You can get pretty deep, get pretty thick a little bit later, but that's really like a little bit engine performance, but we'll cover a little bit of that, probably electrical too. Cool, so visualizing that, now you understand the concept. Like, I would sum most of this up as the allowance thing. If you add resistance, that resistor is going to consume some of that voltage proportional to its size and strength, which is measured in ohms. Okay, and then I think you guys probably mostly get it. We talked about the good conductors. Actually, I didn't go quite far enough. I meant to be here. Now I want to point out another thing. If the resistance goes down, the amperage goes up, right? The current goes up. That's part of the reason that we need to have these fuses or these circuit breakers. So if we were to decrease resistance and the amperage were to go up, it could exceed the rating of that wire, which is why we have a fuse or a circuit breaker. So in this case, it's a circuit breaker, and this one is probably a PTC type where if this starts to get too many amps, this will actually heat up, and rather than having 0.2 ohms, 0.2 ohms is no biggie, right? If it has a full, let's say it were to add more ohms, it could start dropping like full volts. So let's say we were to go back to that that talk of the allowances. Parents give out $12. Let's say, I'll make this a way you can really understand it. The first sibling is expecting to get all 12, but unfortunately, there was a second unknown secret sibling that wasn't really expected to be here, and all of a sudden that sibling's like, hey, yeah, give me like two volts of that. It's unwanted resistance. Like, for example, a circuit breaker. If a circuit breaker is a problem, this is causing a 2-volt drop. Now you have your first sibling not getting the $12 allowance. How much are they getting? Only 10. So if that's a bulb, that's dim. If that's a motor, that's slow. If that's a heater, that heater's not getting hot enough, right? So it's a lot of it's about unwanted amounts of resistance. In this case, it's a circuit breaker that has maybe like bad contacts. 0.2 ohms would actually cause it to drop it'd be dropping closer to 2 volts. Cool. And then your load is not getting access to the full voltage. Just making sure you understand the relationship, not necessarily the math. Cool. Okay, and then one of the final things we discuss is going to be how we measure it. Volts, amps, ohms, now you got those, right? You got the tattoo, you got the relationship, you got the description, but we need to be able to measure those. Remember, so the voltage is the potential, and it's the pressure difference between 2 points in an electrical circuit. That's critical because we have a meter right here that has 2 leads. So if you want to measure the voltage differential between 2 points, how do you pick the 2 points?
Positive and negative.
Yeah, if you want to measure the battery, here are the 2 points. Here and here. So you put 1 lead here and 1 lead here. So your lead placement is all about what you want to measure. If you want to measure the potential voltage difference between 2 points, you have to put one somewhere and one somewhere else. The standard would be put this negative lead on the battery terminal that's negative, and put your positive lead on whatever you want to know how much voltage it has. So if we were to jump to that circuit we made back here, let's say this one, if you want to know how many volts are available here, you'd put your negative lead on the ground, and you put your positive lead going into the bulb right here. That will tell you how much voltage is available. Make sense? How much voltage is available to that bulb? You're expecting $12 to be passed down, correct? 12 volts, right? How do you know if the 12 volts is getting there? All right, cool, right there. Boom, I got 12. What if you only had 6 right here? What's that tell you? Somebody's skimming cash off the allowance. Apparently there's an unknown brother. And if it was 6, it's probably a brother that's got the exact same resistance of 10 ohms. There's a 10 ohm thief in there somewhere. Make sense? So understanding just a little bit about how we're measuring voltage. Now, what if you were to do negative lead here, and you were to put the positive lead right here, and you were to get 6? That's kind of weird. Why didn't this load take all 6 of the volts? It's leaving 6 for someone later down the line. Make sense? That one's gonna be tough for you to get, I'll bet you. But if you got it, you're already ahead. If there's 6 leaving the bulb, that means this one didn't consume all 6 because it's expecting someone else down the line to be getting their 6 cut. That means there's unwanted resistance down here. So real quickly, you could tell if the problem's up here, it's only getting 6, or if it's getting a full 12, but it's leaving 6 left over, the problem's down here. Make sense?
Yeah.
No. Maybe? All right. If you got a little bit of that, you're ahead of the game. Cool. But don't worry, you'll get it in the next couple of weeks.
Alright, bro, so the thing shows, the negative should always say 0?
The negative should say as close to 0 as possible, and that tells you got a clean path to the ground. If the negative shows more than that, that means there's resistance on the negative side, and that does happen, by the way. You can have a dirty ground or when something doesn't work, you think in your mind, does it have power? And you're right. Power, right? If it doesn't have good voltage, it's not going to work. But this is where people get bit. If it has good voltage, but it doesn't have a good access to ground because there's resistance, it'll cause the same types of problems, but it's on the ground side of the circuit. Make sense? Problems in the positive, problems in the negative, both problems. Still got to be able to diagnose both. Cool? And then we talked about kind of how to hook up the meter. And there's going to be another thing that I'll show you with the meter. It's about available voltage and voltage drop, but that's a whole, that's going to be covered on its own. Okay? Then we talk about amps. The amp, or the ampere, describes how much current's going through a given point. So, for the record, 1 amp is equal to how many electrons you think? 6.28 billion electrons traveling past a given point in a circuit in 1 second. So remember I told you electrons counting it like this? 1, 2, yeah. It's a lot faster. A lot faster than that. So if you have an amp, now you know that's a quantity of electrons in 1 second. It's like, all right, start the timer. 1 Mississippi. Yep, I counted it. 6 point how much? 28 billion. Light work. You know, that's what your meter does.
So being electrocuted is so much fun.
And you can, if you can count each one, even just 1 amp, you got a lot of electrons going through there. Make sense? And then remember, it can be measured either by placing an ammeter in series. So an ammeter is a function of your multimeter. You put it in series, right? We break the circuit open. We make it go through the meter so it can count them. That's normal. Or it's saying also, sometimes you can do an inductive probe or inductive clamp, like I had said earlier. And those are close, not exact. The probe itself will tell you how close it can get you. The expensive ones can be pretty close. Cool. And then there's ohms. So using the meter right here, ohms is a unique measurement. By the way, we're going to cover this 3 times. So when we put it on ohms, you're going to have the leads in these 2 spots. When you have it on amps, you actually have to move the lead over here. And the reason why is because this one goes through a fuse. Now each meter can be different, but it's pretty standard that the amperage port will go through a fuse because you don't want to hook it up in series and then have too many amps go through and have it melt your leads or ruin your meter, right? So they fuse it, and that's the fuse that you can blow. But when we're back to measuring ohms or resistance, I want to explain this in a way that helps you understand it. Your meter has a 9-volt battery inside. When you go to measure ohms, what it's actually doing is it's using its internal 9-volt battery, and it's going to send electrons out from its 9-volt battery and go through your component, in this case an injector, and then they're going to come back and it's going to basically give a number of how difficult it was to do that path. 2 ohms would be like, oh yeah, there's some resistance there. This is 16.2 ohms. That's more resistance. That means, hey, on your journey from the red all the way back to the black, like it was kind of difficult. 16 ohms is like 16.2 ohms is more difficult, right? That's how it measures the resistance. It's how it measures. Remember the resistance, like that corrosion and stuff? If we were to have corrosion and damage inside here, it'd become more difficult, wouldn't it? The ohms number would go up. Cool? So we're testing an injector. If you want to test an injector and it said the spec is 4 to 8 ohms, and you measure at 16.2, what do you determine?
Too much resistance.
Too much, it's excessive. You know, and you could document that in your notation and say, hey, I measured the resistance of this injector with 16 ohms, that's a fail. I replaced the injector and it fixed it. There you go. Bada bing, bada boom, how you doing? Like that. Okay? But that's how it does it. So the thing that gets people messed up, because you're using this internal battery, you got to have this disconnected. You can't have that injector hooked up and powered up and things because it's going to throw the measurements off. So I've actually seen stuff with a negative resistance. If you show me a measurement with negative ohms, I know that it's not only easy for those electrons to get back, there's more of them coming back, and it's even easier than easy could possibly be. Oh, that's because your circuit is on and there's other electrons in there. Make sense? So when you do this resistance measurement, It's gotta be isolated from the circuit. You can't have it powered up. You can't have it, you wanna test that bulb, you can't have the headlights turned on and testing the bulb. Doesn't work that way. That's the biggest thing with checking resistance. It's not really a very difficult thing. They may call it an ohm meter. An ohm meter measures ohms. The reason that this is a multimeter, it's a voltmeter, it's an amp meter, it's an ohm meter. It can even do some other stuff. And it's digital, so that's nice. Okay, looks good. And then, when we get into the basic circuit, which we're gonna start building probably as soon as next week. That'd be fun. It has to have a power supply, maybe the battery, but maybe not. Could be something different. In the house, it's something different. A fuse, a switch, and a component that performs work, and wires. So we'll break them down step by step. The power supply. What's the power supply in the car?
Battery.
Battery, yeah. Now when it's running, it's kind of the battery, but it's kind of the alternator, just for the record. And that's why when Ronnie was saying, hey, if I want to do my big system and whatever, your alternator has to supply enough amps to power that system. If it doesn't, and you're doing the boom, boom, bang, bang, it'll be drawing your battery down, and your battery will be dying as you drive, and that's not good. Exactly. So there's kind of two power sources. A fuse, you guys know where those live? In the fuse box. Yeah, there's a whole bunch of them.
In a box.
A component that performs work. What?
Battery?
The battery doesn't do the work, it stores.
Starter.
The starter motor, the bulb, exactly. What else? What
The
else?
alternator?
The alternator doesn't really do work though.
No, it doesn't.
Close,
Radio?
close.
Radio?
The radio, think of things that,
Airbag.
okay, pause right there. If the airbag's doing work, that's not good. Okay, but yes, that's true. It is, that's a component. What about
Dash,
Air conditioner.
any of those lights in the dash? The AC kind of. The AC does have a clutch. That does electrical work, but then most of the AC work is pulled from the belt, the engine.
The meters, like my fuel.
All
and
those
things
are
like that.
little electrical loads. Who used anybody heated seats? Definitely. Yeah,
Oh,
so
electric power
in the
seats.
circuit, all those things are the load, right? We got to bring the electricity there though. So how do we get the electricity there? The wires. Cool. So you have a source of power, the battery. You have wires bringing them to the component that does the work. It toasts your buns. It makes your ears happy. It makes you be able to see. All these things do work, and they do it all for you. All just for you. At the command of a switch and things and whatnot. But when they don't do what you want, you bring it into the shop. And so that's why for me it's hard to be super passionate about cars, because people don't bring me a car and be like, just check out this amazing car. They're like, hi, it's broken, make it work again. And I'm like, oh, cars to me, cars equal problems. Period. Because that's the only reason I see them. But the good news is people will exchange tender, that's money, which generally I accept in what's called greenbacks, and cash money. Don't you give me, I don't want any of those bitcoins and the other baloney, right? So they'll take my time and I'll solve their problem and I'll take their money.
That's
And
like
it'll
you
be,
use Australian dollars.
what do they use?
I have no fucking clue.
Australian dollars
Okay,
is what it's called.
now understanding this, okay, very good. Let's go with, sorry, I jumped a little bit too far ahead. Here's what that looks like. Here's your battery, 12.6, positive. Here's a wire, right? Here's a fuse to protect it, lives in the fuse box. Here's a switch. This is something we didn't talk about exactly. Here is the load. What is the load? I don't know. Heated seat, headlight, I don't know, whatever. Fuel pump, you name it. Starter, a load. And then it has to have a path to the ground. Now, what the heck is the switch, though? What does the switch do for you? Remember, it's
Turn
all
it on and off.
It's control, exactly. So if you ever hear the term control, the control is like a way that you can control the load. If it's your headlights, you want to turn them on, control the switch. Turn on or off the switch. Headlights, that'll do that. If it's the heated seat, turn on or off the heated seat. If it's the starter motor, Sha-na-na-na-na-na, right? This controls the current flow, and this does the work, and the wires carry the electrons. That's the simple circuit, right there. And then this is just kind of like describing, if it's a filament, it heats up, the current continues to flow. I think this is the wordy version of what I explained in this one, right? So the voltage is the pressure, pushing the amps, pushing the electrons. There's a certain amount of resistance. Where's the resistance in this circuit? Not quite. It shouldn't be. The load. The load should have the resistance. The load is like the, remember in the family pecking order of allowance? Who gets the money? Well, if you're the only one, yes. The load takes the cash, right? The load takes the voltage. That headlight takes the 12 volts. Now, unfortunately, if the switch is also having some resistance, then the switch takes 1 volt and the load only gets 11 and stuff, whatever. But this has resistance, and it needs to have resistance, and it should have resistance. And that's normal. You want to pay, basically you're paying voltage dollars to the load to give you light, heat, something, whatever. You don't really want to be paying this switch. This switch is just supposed to be controlled. The switch shouldn't take really a substantial toll to use the road. These are cheap. Make sense? Okay, and then tell me about amps. What are the amps here in this circuit?
The flow.
The quantity, yeah, exactly. So the amps are like basically the number of electrons that are going through. You can't see those, you gotta measure them. Makes sense? So to apply volts, amps, ohms, volts is the push. Remember, resistance is kind of the resistance to that, the slowdown, which is the load, hopefully, only, maybe. And then the amps is the quantity of electrons flowing. That's how you apply all those in a circuit. And if everything's going well, this circuit will work great, and your load, whatever that will glow or be bright or be dim or whatever.
It'll be simple.
It'll be correct, whatever that is. And then the last thing we'll cover is we're probably pretty good on the basics. The semiconductors we're going to chip away at. So we talk about the electronics, right? Devices which electrons are conducted through vacuum, gas, or semiconductor. So that's, let's say mainly we're talking semiconductor. Back in the day, they used to do some other different things with bulbs and vacuum and stuff. But the semiconductor electrical resistance is higher than that of conductor but lower than an insulator. And then again, conducting ability depends on 2 kinds of charge carriers, the negative electron or the hole. So if we were to take a big look at this, you would have your, let's say you talked about that switch, right? That switch, how do you control that? The light switch, like this, correct?
Mm-hmm.
Well, who's got a car that the headlights turn on and off automatically? Anybody? Some of you got auto headlights. I know you do.
Well, mine turn off automatically.
Okay, cool. A lot of them, if you put them on auto setting, they'll turn on, they'll turn off. So now I want you to zoom out for a second. If it's dark outside and you're trying to sell the fanciest, latest, and greatest car and you want the headlights to turn on automatically, what are you going to do? You're going to hire the trunk monkey to jump out and turn the light on for the customer?
What else am I paying a month for?
I think security. Not exactly sure.
Wouldn't it be the switch?
So it was the switch, but if you want to go to like an automation system or like a more advanced system, you don't actually turn the switch, right? That's when we get into the semiconductors. The semiconductors operate in a way where we can use a computer to basically make the current flow. So you remember we had that switch back there, and there was a physical, you can see this is the switch. Your hand goes like this, click, click, click. Computers really, they're not good at moving that. That's hard to move, that takes work. Computers are weak, they're fast, but they don't handle a lot of current flow well. So we get into semiconductors and electronics, and rather than having this switch, we'll put like a solid state switch or like a transistor, and we can basically make it function so that it's an insulator, and that's like an open circuit, right? If the circuit's open, what's the light doing? It's off, yeah. But what if it's a semiconductor and it's constantly connected? There's no open and closing method. There's just, it's an insulator, or at the flip of a computer micro switch, all of a sudden it's a conductor. What happens to the light? Exactly. So when you hear the term solid state, there's not clicking, there's not levers, there's not moving, there's no trunk monkey, there's no elf in there, there's no little trolls and
No
stuff.
dribbles on the road.
Nobody does that type of stuff. It's the computer using semiconductor electronics. Hey, rather than insulate that circuit, conduct it. Boom, and now your lights are on, right? The computer can function in that type of a workplace.
Somewhere there's a sensor telling the computer in the dark, right?
Now, if you really want to get super technical, yes, we have a sensor that's usually in the dash. It's a bubble. We'll call it like an ambient light sensor, a solar sensor. They vary, right? That's an input to the computer. The computer's got programming. Then the computer's like, oh, it's dark outside. I know what to do because my engineer programmed me, kind of like some of you have programmings. If you don't believe me, go ahead and test this. How'd you know to do that, dude? Because you saw it. You were kind of programmed to be like, I don't want to get hit in the face. And so then you're like, throw my hands up, right? The engineer programs the computer to say, if that light sensor shows it's dark outside, go ahead and make this conduct and turn the lights on. Cool. So that's electronics. But there's not moving stuff. It's just, it's solid state. It doesn't move. It doesn't, it's cool. So that's pretty much, I'm going to say, let me kill it right there, and we'll do some stuff. Or left, will you?